Welcome back, Vulkan devs. In the first video, we went through initializing our Vulkan window, our shaders and graphics pipeline, and ended up drawing a static triangle to the screen. While this is a big milestone when starting out with Vulkan, it's objectively pretty boring and probably not what any of you imagine when you think of graphics programming. In this lesson, we'll bump up the quality substantially by loading and drawing a full 3D scene with our Vulkan renderer. To achieve this goal, we'll need to focus on the following subjects: understanding, parsing, and loading various resources described by GLTF scene file, creating buffers and uploading data to the GPU such as geometry and texture data, implementing various structures to represent a 3D scene within our renderer, creating a basic orbit camera so that we can actually look at our scene from various angles, and as a bonus, we'll quickly look at how to implement a directional light so that we don't have to stare at a flat, ugly colored scene. If you're new to Vulkan and haven't watched the first video where we set up a modern Vulkan renderer in 2 hours, be sure to go through that first as it lays down all the groundwork you'll need for this video. With the agenda out of the way, let's get started. We'll kick things off with GLTF, as it's the 3D format I've chosen to focus on in this series. For those of you who haven't heard of GLTF, it's a 3D interchange format specifically designed to be open and easy to integrate into just about any 3D application. If you've worked with 3D tools like Blender, Maya, or Max, you've probably used FBX, which is another very popular 3D interchange format. Unlike FBX though, the GLTF specification is fully open, which means if you wanted to, you could write your own parser without much trouble. In the past, I've done just that for most of my hobby projects. For our purposes, we'll be using the TinyGLTF library, which is super lightweight, easy to integrate, and overall fantastic. As of the making of this video, TinyGLTF has seen an update to version 3, which changes the API significantly, moving closer towards a standard C API that can be used on any platform where C code can be compiled, making it a great choice for almost any project and on any platform. Before looking at any code, we should first look at how scene data is described inside of a GLTF file. Understanding the format is critical as we'll be using it to bring in all kinds of assets into our game project throughout the series, such as environment art, characters, props, cameras, bones, and scene animations, and even gameplay properties. For this lesson, we'll only care about the parts needed to represent a scene in 3D. This includes scene nodes, meshes, textures, and materials. After watching this video, it's a good idea to read and bookmark the official GLTF2 specification. It's super easy to follow, making it the best resource for anyone wanting to understand GLTF in depth. GLTF comes in 2 flavors: self-contained GLB files, which contain all assets and resources in a single file, and a split-up version with a human-readable GLTF JSON file, which references the binary files and texture resource alongside it. I highly recommend working with the GLTF JSON format as you start, as it lets you read the JSON data and easily open and view textures without having to deal with the packing of GLB files. When you get to a point where loading speed is more important, you can switch to GLB. To understand the GLTF format, we should start with a high-level diagram. At the top, we have the notion of a scene, which is just a container holding the indices of the root nodes of the 3D model. All resources in GLTF are referenced by their index within their respective list in the document. This includes meshes, materials, nodes, textures, images, etc. Nodes are the main star of the show and are the building blocks of the scene. Each node can contain a list of child node indices, which is how we describe complex scene hierarchies. Nodes also tell us how they should be transformed by providing either a set of translation, rotation, and scaling fields or just a single transformation matrix. These transformations are always relative to the node's parent, and it's our job to ensure that nodes are properly transformed during rendering. We'll look at how that's done later when we actually traverse the scene and render everything. Nodes can also contain a mesh index, a camera index, or a skin index for skeletal animation, each referencing a different object in the document. For this lesson, we'll focus on the mesh objects, which are themselves further broken down into what GLTF calls primitives. These are the smallest drawable objects in the scene. Each primitive has vertices, indices, texture coordinates, and other geometry data which is stored separately in binary files, referred to as buffers. The location of the primitive's data is defined by BufferViews, which split up the binary data into various sections. The specifics on how to load a particular attribute are defined by the attribute's accessor, Accessors specify a byte offset inside the buffer view, as well as the number of elements to load. The type and component fields tell us the format of the data, such as vectors, matrices, and scalars. Having the data described this way makes loading it quite trivial, especially since TinyGLTF will actually load the buffers for us, letting us simply traverse using simple pointer arithmetic. As I mentioned, primitives also index into the materials list, telling us what material we need to use when we draw them. The GLTF specification covers full PBR materials, which can use texture maps for diffuse or color, normals, roughness, metalness, ambient occlusion, and emission. For this lesson, we'll look at the diffuse or color maps, and since we're only doing simple directional lighting today, we won't be using any of the other texture maps just yet. We'll come back to this in the upcoming lighting video. A material refers to its various texture maps by indexing into the textures list. A texture is used to define the combination between a sampler and an image source. Samplers describe how a texture should be sampled during shading, and contains fields for controlling the magnification and minification filters, as well as texture wrapping when the UV coordinates are outside of the normalized 0 to 1 range. The texture source field can contain an index into an image object describing how to load the image data. This can be either a direct URI to a file or a buffer view describing the image data location in one of the GLTF buffers. You'll almost always use the URI here though. We'll look at everything here in a lot more detail as we go through loading the model. But for now, I just want you to have a general idea of the various GLTF concepts that we're interested in. To get started with TinyGLTF, download the latest release from the official GitHub and extract it somewhere on your drive. Then add TinyGLTF JSON.h and TinyGLTF v3.h somewhere in your project source code, and make sure your build system knows how to find them. As always, I'm using CMake, so I've created a folder called ext for external and added the files there. After this, it's just a matter of setting the target include directories in my CMake list.txt and ensuring the folder path is added in there. TinyGLTF is a header-only library, but we need to ensure it generates its implementations during compilation. The easiest way to do this is to create a CPP file that will contain those implementations. I've created a file called tinygltf.cpp alongside the headers we just added, and included it to my list of compilation units in CMake. Inside that file, we'll need a few preprocessor defines to ensure TinyGLTF emits everything correctly in the CPP file. Just define tinygltf3_implementation for the implementations, tinygltf_enable_fs to get the binary files loaded from the file system, and tinygltf3 enable STB Image to have the embedded image data decoded during model loading. The last macro will only decode embedded base64 images that are directly stored in the JSON document. We're going to manually load our images because that's the kind of control we want anyways. And speaking of images, as you've probably guessed, we'll be using STB Image to load the images into RAM. To set up STB Image, the process is identical to what we just did for TinyGLTF. Grab the header from the official STB GitHub, save it into your project, make sure your build system can find it, and add these two lines in the CPP file we created to ensure that the STB Image library also emits its own implementations. Remember that you should only define these macros once in the entire project. When you want to use TinyGLTF or STB Image in your actual code, you only include the headers without defining these macros again. Last but certainly not least, we need to ensure GLM has been added to the project. If you opted in to install GLM along with the Vulkan SDK, you can probably just start including the headers since the Vulkan package should add those to your include directories. If not, you can download the latest GLM release from the GitHub repo and add it to your project the same way we just saw. If you run into any trouble here, check out my game development with SDL3 video. I have a section dedicated to adding GLM and other libraries to the project, and I'll put a link in the description. With the boring library stuff out of the way, we can start talking about how to use TinyGLTF to load a scene into our renderer. If you don't have anything made or are looking for a model to test with, take a look at the GLTF sample models repo on GitHub. There's a ton of content there and lots of stuff to play with. Sketchfab is another great source. Just filter by downloadable and search something like game levels. The first thing I want to show is a small change to the application's main function. I've added a call to a method named loadData, which is where we'll allocate memory for the scene and load all of the resources needed for rendering. In the future, we're going to want to allocate and load game resources differently, such as preloading certain assets and loading others per game level, for example. For now though, we just need a place to prepare everything before we start rendering frames. Shifting our focus over to the loadData method, before we can actually load any model geometry, we'll need a place in RAM to store all of the vertex and index data that we're going to load for our scene. All we're doing here is allocating two buffers, 64 megabytes for the global vertex buffer and 32 megabytes for the index buffer. Memory management in games is a pretty big topic and will become much more relevant as our project becomes less of a simple renderer and more of an actual game engine. For now, we just need to store the scene geometry in RAM before we can begin the process of uploading it to the GPU's video memory. Our buffers are just two vectors in the application class, one that holds vertex elements and the other unsigned integers. Once we have those sizes in bytes, we can divide each one by the vertex or index sizes to get the total number of elements each buffer can hold. We then use those sizes to resize the vectors accordingly. With the CPU side geometry buffers allocated, let's start loading the scene assets. The next section isn't often taught, but I want to show it as it serves as an excellent high-level overview of how image data is uploaded to the GPU. What we're doing here is creating a single white pixel image texture. The reason is quite simple. If our shader encounters a material that doesn't have a color image texture assigned, we can fall back to this little texture as the color. The alternative would be branching inside the shader code, which is generally frowned upon, though less so these days. We'll look at the shader code in a bit, but for now understand that this is a fallback texture. What we have is a 32-bit integer representing a single opaque white pixel. This will serve as our image data. We then create an instance of the image structure, setting the width and height to 1 and the number of color channels to 4, since we're using RGBA. The image data pointer is assigned the address of the integer above, and we're ready to upload into VRAM. We haven't yet looked at how data is copied into video memory since our triangle data was just hard-coded into the shader. This can feel kind of tricky at first, but it's really not that difficult once you understand the pieces involved. In a production game, you'd probably create separate I/O threads and ensure that you're leveraging the GPU's transfer and DMA features to load data seamlessly. I promise we'll get there as the series progresses, but doing all of this right now would introduce unnecessary complexity. All we want for now is to be able to upload our assets into GPU memory where our shaders can access them. So let's see how that's done. Image and buffer copy operations in Vulkan are generally commands we record into command buffers. What that means is that we can't just call a copy function and expect our data to be uploaded immediately. We need to create a command buffer, record those commands into it, then submit it to a queue and wait for it to complete. Before I show you this though, I'd like to take a second to address the host image copy extension, which was added into Vulkan 1.4 core. You have some buffer with image data sitting in RAM, you want to upload it into video RAM, and don't want to deal with the whole command buffer song and dance. Great, except support for this extension is still pretty spotty. In fact, the video card in the machine I'm working on here, a Radeon RX 6750 XT, doesn't yet have support for this extension. Perhaps AMD will solve this with an upcoming driver, but for now, I'm stuck without it. The 4070 in my laptop, on the other hand, does have support for it. Regardless of device support, it's important to understand the more complicated version of this process, as that's certainly what you'll eventually want in a production game engine. If you want to check whether you have support for this extension, you have to do it during device creation and then make sure you have it enabled. Actually using the extension is fairly well documented in the Vulkan docs, but I'll have a block of code in the repo showing what that looks like. To copy our image data into VRAM, we first need a command buffer where we can record our commands. The start transient command buffer method will create one for us. We've seen how to create command pools and buffers before, so we don't have to spend too much time here. The only thing to remember is that we're creating a new command pool in the create command buffers method, which we're using strictly for these one-time use command buffers. This is denoted by the vkCmdCopyBufferToImage create transient bit, letting Vulkan know that the allocations made using this pool are going to be short-lived, allowing the driver to perform certain optimizations. Don't forget to also destroy this pool at the end of the application inside the shutdown method. To actually get our transient command buffer, we first allocate it from the command pool. fill in a vkCmdBuffer allocate info structure to create a primary command buffer, then call vkAllocateCmdBuffers, passing in the struct and getting back our vkCmdBuffer handle. We also want to begin the command buffer before we start using it, which we can do using the vkBeginCmdBuffer function. It takes in our new command buffer handle and the address of a vkCmdBuffer begin info struct. Just like in the previous video, we use the vkCmdBuffer usage one-time submit bit to ensure that this command buffer can only be submitted once to a queue before having to be reset. Finally, we can return the command buffer handle, and it's ready to be used in the calling method. Back inside the load data method, we can call the create image method, which will create our vkImage, vkImageView, and record the required commands for uploading the data to the GPU. We've seen how vkImage and ImageViews are created when we created the depth image buffer, so this shouldn't be unfamiliar. We start by creating an instance of the vkImage create info structure. We set the image width and height, which we passed in as arguments to this method. We also have just a single MIP level, a single array layer, and no multi-sampling. The tiling is once again set to vkImageTilingOptimal, which is what our shaders will prefer when sampling. The usage flags need to be vkImageUsageTransferDestination bit, which tells Vulkan that this image will be a destination for a transfer operation, as well as the common vkImageUsageSampled bit to ensure that the image is suitable for sampling in the shaders. The initial image layout can just be set to undefined since we don't want Vulkan doing any validations on any existing memory in the image after creation. The VMA allocation create info structure will tell VMA that we want it to automatically pick the appropriate memory type and configuration for us based on the properties we just specified. The allocation will happen in VRAM, which is exactly where we want our textures to be. We then follow this up with a call to VMA create image, passing in the VMA allocator, the image info, the allocation info, and the address of a vkImage variable to receive the image handle. I've created this GPU image structure which will help keep image-related data together in a single place so that we don't end up needing multiple lists to keep track of all this stuff. It holds the vkImage where we're storing the handle, the vkImageView, which we'll create in a second, as well as the VMA allocation handle that we'll be using to clean up memory during shutdown. The vkImageView object's job is to describe how our image data is to be accessed during rendering. Shaders don't access that image data directly, so we need to create a view into the image memory, which is what we're doing here. We're telling Vulkan to view the image as two-dimensional data with the same image format we specified above. The sub-resource range states that we'll be accessing the color image aspect of the vkImage and only looking at one MIP level and one array layer, which is all we have here anyways. Next, we can call vkCreateImageView along with the ImageView info and the address of the ImageView field inside of the GPU image instance. With the image memory allocated, we need to prepare to upload our image data into the vkImage. For this, we need to set the image layout to vkImageLayoutTransferDestinationOptimal. This prepares the hardware for writing into the image and ensures any data in the GPU's caches that needs to make its way into the image is flushed and visible in VRAM. This ensures there's no pending data and it's safe to overwrite the image memory. You might be asking, why didn't you just set the initial layout of the vkImage to this layout directly instead of using a barrier after the fact? Vulkan requires images to be created in either the undefined layout, which is what we're doing, or the pre-initialized layout. If we decided to create the image with the pre-initialized layout, we'd be telling Vulkan that we intend to write the image data directly using the CPU. But this brings up a couple of important points and segues into an important lesson. In order for the CPU to write the data and for the GPU to be able to actually read it, it has to be written into a region of memory called the resizable bar. For historic reasons, this area of memory can be quite limited and should be strictly reserved for smaller data that needs frequent updates by the CPU. Our model textures or meshes don't need to be touched by the CPU, so they're certainly not good candidates for this heap. That being said though, modern system configurations can expose the entire video memory to the resizable bar, but this isn't guaranteed and we won't be relying on it. The second issue is that in order for the CPU to write the data directly, the image tiling must be set to linear, not optimal. And as you already know, optimal tiling is what the GPUs prefer for sampling. So linear tiling would end up crippling the performance of our fragment shader. Since we aren't waiting on any commands inside of this transient command buffer, we can set the source stage and access masks to none. The destination stage should be set to VK pipeline stage 2 copy bit, and the destination access mask should be set to VK access to transfer write bit. This ensures that the image layout transition that we're performing using this barrier fully completes before the copy operations, which we're about to record, can actually start executing. To record the barrier in the command buffer, we create a VK dependency info object and point it to the VK image memory barrier 2 object we just created. Then we just call VK command pipeline barrier 2 with our command buffer handle and the address of the dependency object we just created. Now it's time to move on to copying the data. The way this will happen is we'll create a VkBuffer in system RAM in order to stage the data for copying into VRAM. Since we can work with system RAM allocations directly, we'll map the staging buffer and get back a pointer to it, allowing us to memcpy directly to get our image data into it. Once our staging buffer has been prepared, we'll record a copy command in our transient command buffer that will actually do the copy from staging into device local VRAM, which is the final destination for the texture data. Before we look at this in more detail, let's take a look at the call to create buffer. Note that this method receives some parameters, including the buffer usage flags, which we're setting to VkBufferUsage transfer source bit, telling Vulkan that this buffer will be the source for a transfer or copy operation. We also pass along the buffer size in bytes and pass true for the mappable parameter, which will ensure that we can map and get back the pointer to this buffer, which is how we're going to memcpy into it. Then there's the VMA memory usage flag, where we're saying we want this buffer to be strictly in host memory, which just means system RAM. Creating the VkBuffer is pretty straightforward. We start with a VkBuffer createInfo object, where we pass along the requested buffer size, as well as the usage flags the method received. The sharing mode field tells Vulkan whether this buffer will be accessed between multiple queue families concurrently. We're only using a single graphics queue, so we set this to VK sharing mode exclusive, meaning that our graphics queue family is going to have exclusive access to it. This gives Vulkan a guarantee that this buffer will not be shared, allowing it to make certain optimizations. If we did want to share this buffer between queues, we'd use another pipeline barrier and perform what is called a queue family ownership transfer. We're not doing anything like that just yet, so we'll just set it to exclusive here and move on. Once again, we're using VMA to handle most of the heavy lifting during memory allocation, which is done by creating a VMA allocation createInfo object. For the flags field, we pass in VMA allocation createHost access sequential write bit, but only if our mappable parameter is set to true. What this flag means is that we intend to map this buffer and write sequentially into it, which is exactly what we need for the memcpy function. This is a lot like linear layout for the vkImage object. If we had passed in false for mappable, the flags field would get a value of 0, telling Vulkan that we never plan to map and access this buffer on the CPU. For our current buffer, we're explicitly asking for system RAM storage via the VMA memory usage auto prefer host flag. When we want an allocation from VRAM, or as it's called, device local memory, we'll be using the VMA memory usage auto flag. An auto flag here coupled with host access sequential would create memory that is mappable and accessible from the CPU, but resides in VRAM. This means that we would end up using the resizable bar memory that we spoke about earlier. If there was a value of 0 in the VMA allocation flags, we would get a pure device local allocation completely inaccessible from the CPU. To perform the memory allocation, call VMA createBuffer with the VMA allocator, addresses of the buffer and allocation info objects, and the addresses of the vkBuffer and VMA allocation fields in the GPU buffer struct. We're using this struct to group Vulkan buffer related fields together. We have the vkBuffer handle, the VMA allocation handle, and a 64-bit unsigned integer, which can hold the video memory address of this buffer. We can ignore the following section here, as we'll come back to it later when we use the createBuffer method to allocate buffers in video memory rather than system RAM. It's at this point that the buffer device address section here will really be interesting. Since our staging buffers are being created without the VkBuffer usage shader device address bit, this section of code will just be skipped and our GPU buffer object will be returned to the caller. Now that we've created the staging buffer in system RAM, we can call the memcpy method to retrieve a pointer to the staging buffer and copy our image data into it. The method takes a few parameters. First is the newly created GPU buffer representing the staging buffer, followed by an integer representing an offset into that buffer. In the future, this will let us write data into our buffers at different offsets. For now, I'm just passing 0 here to signify the start of the buffer. Next is a pointer to the image data we received in our current createImage invocation. You'll recall that this is just the address of the 32-bit unsigned integer representing our 1 pixel by 1 pixel white fallback image. And of course, we also need the size of the data in bytes, which we also received via parameter. The method itself is very straightforward. First, we call VMA map memory to get the address of the start of the buffer's memory. This requires the VMA allocator, as well as the VMA allocation handle, which we have in the GPU buffer object. VMA maps the buffer and stores its memory address into a void pointer we provide in the last parameter. Once we have the address, we can make a regular memcpy to get the image data into the buffer. The destination address is the buffer address offset by the buffer offset parameter we received, which again is just 0 at the moment. The source data is just the address of our image data, and that's followed by the number of bytes we wish to copy. Once the data is copied, we can simply unmap the buffer and our job here is done. Now that the staging buffer is populated with image data, we're ready to record the command that'll make the final copy into the vkImage sitting in GPU memory. For that, we need to call vkCmdCopyBufferToImage. The first parameter is the command buffer that we're going to record into. The second is the staging buffer's vkBuffer handle, representing the source of the copy operation. The third parameter is the destination vkImage that we're copying into. This is followed by the image layout that our image is currently in. During the copy operation, the vkImage layout can only be in one of the following 3 layouts: presentation, transfer destination, or general. Of course, ours is set to transfer destination, so we specify that here. We need to tell Vulkan the layout here for a couple of reasons. First, Vulkan uses it to perform validations before the copy. More importantly though, in order for the copy to occur, the hardware needs to ensure it's copying our linear buffer data correctly into the image memory location. The transfer hardware in the GPU needs to be configured correctly to match the byte order of the destination image. And for that to happen, GPUs have specialized hardware which performs a byte reordering technique called swizzling. With the layout specified here, Vulkan can configure the hardware correctly to ensure that the bytes are copied in the correct order. Next, we specify the regions of the image we wish to copy. We can provide any number of regions here, but since we're doing a single full copy of the image, we specify a count of 1 and pass the address of the VkBufferImage copy object above. This struct specifies the usual image sub-resource, which includes the vkImageAspect color bit, and specifies the first MIP level and first array layer of the image. And the extent specifies the width, height, and depth of the image. We set the depth to 1 for standard 2D images and only really use this field for 3D volumetric images, which we're not interested in just yet. Since the image will eventually be sampled inside of a shader, we can't leave it in the transfer destination optimal layout. We need to transition it into a layout suitable for sampling. You guessed it, we have another pipeline barrier. This time, we ensure the source stage mask is set to VK pipeline stage 2 copy bit, and the source access mask is VK access 2 transfer write bit, which will ensure that any writes from a copy operation complete before the layout transition. The barrier's destination stage and access masks state that we want all reads being performed during a fragment shader stage to wait on the copy write operations to complete before allowing any sampling from the image. Once all of the copy write operations have completed, the image is transitioned from the transfer destination optimal layout into the shader read only optimal layout, which is what we need for sampling. We of course have to specify the vkImage that we want to transition and the usual sub-resource range for the single MIP level image. Like before, we create a vkDependencyInfo object and point it to our barrier. Then once again, we call vkCommandPipelineBarrier2 to get the barrier placed in our command buffer. And with that, we now have our copy command recorded, immediately followed by a barrier, which will ensure that our staging to VRAM copy completes and our image's layout is transitioned appropriately. At this point, the VkImage and its associated image view and VMA allocation have been created, and the staging data is scheduled to be copied into it. What we want to do now is keep track of our GPU image in the application so that we can use it during rendering and clean it up when the application terminates. This is done by simply pushing the GPU image object into the images vector in the application instance. But before I explain how we use the image for rendering, let's quickly go back to the GLTF structure for a minute. Recall that to render a GLTF primitive, we first need the material that's associated with it. Each material can have various texture maps. Each texture is associated with a loaded image as well as a texture sampler. All of these things will have to be able to connect and refer to one another for this all to work. What we don't want to do is have pointers or references to all of these resources all over the application. This is cumbersome and can be a source of nasty bugs. What we'll do is generate an integer ID for every single resource we load from the GLTF model. Every mesh, material, image, texture, and sampler will have its own unique ID within its respective resource type list. You might be thinking to yourself though, doesn't GLTF already refer to everything by its respective index? Yes, and what we're doing is similar, except ours will be unique across multiple GLTF files, not just within a single model. This means that we'll easily be able to load different models to populate our worlds. This concept will be extended much further with persistent unique global IDs that will be used for our authoring data format in the future. What we're doing now is just generating dynamic runtime IDs whose only purpose is to connect the various pieces together. These are not IDs that you'd be using inside a JSON or XML document that is used for describing your game world. With that explanation out of the way, I'd like to show you a simple approach we're taking to generate all of our IDs today, starting with the image IDs. I call them IDs, but they're really just indices into the resource vectors. The only difference is that I'm using 1-based indices here, rather than the standard 0-based. This means that we can save an ID of 0 to represent a null ID, rather than resorting to using a negative number or some other sentinel value. This makes things super simple. We don't need signed integers, and we get the full integer range. When we want to represent the null value, we just use a value of 0. When we need to access something, we just subtract 1 from its ID to get the index into the respective vector. We're going to do this for all objects today, but we'll improve upon it quite a bit in the future when our scene renderer becomes an actual running game. Nodes and objects in the game world will come and go, and various resources may be loaded and unloaded as the game runs. Introducing object pooling, generational IDs, and free lists will be a must for a real game to run well. To get an ID for our newly created GPU image object, we just use the vector size after the object has been pushed into it. Our first image here will have an ID of 1, and when we want to access it, we'll use its index of 0. Okay, enough about this. It's very simple, but critical for what we're doing. At the end of the method, we return a tuple containing the new image ID along with the staging buffer handle. I'm passing the buffer back here so that we can destroy it after we finish executing the command buffer. The staging buffer needs to live long enough for the data to finish copying into video memory. All that's left now is to submit the command buffer into our queue and wait for it to complete. The submit transient command buffer method will handle this for us, so let's see how that works. First thing we do is call vkEndCommandBuffer to finalize command recording for this command buffer. Next, we call vkQSubmit, which submits our command buffer to the graphics queue. The vkSubmitInfo struct specifies the number of command buffers we're submitting and needs a pointer to the list of command buffers being submitted. We only have one, so we pass the address of our command buffer here. In the vkQSubmit call, we're specifying how many submissions we're making, so we just put a 1 and provide the address of our submitInfo object above. Recording and submitting multiple command buffers is an advanced topic that we're going to revisit when we look at multi-threaded rendering. Finally, we call vkQWaitIdle, along with the graphics queue handle, in order to wait for the recorded commands to fully finish executing. Just like vkDeviceWaitIdle, this function performs a very heavy-handed synchronization and shouldn't be used in production code. That being said though, it's perfectly fine for what we're doing today. But as we'll see in the next couple of videos, we're going to want a more seamless synchronization for an actual game. When this method completes, we'll know that the commands have finished executing and the image data has been uploaded into video memory. All that's left is to free the command buffer now, and we're done. Simply call vkFreeCommandBuffers, passing in our command pool, the number of command buffers we're freeing, and the address of our command buffer. With the command submitted, executed, and waited on, we can be sure that our image is ready for use. Since we no longer need the staging data, we can call VMA destroy buffer along with the vkBuffer and VMA allocation associated with the staging buffer to free the memory we allocated for it. Note that we've also stored the image ID in the application so that we can easily retrieve it later. With this section complete, you should have a fairly good understanding of how we create images and copy data into them using a transient command buffer. This is the same process we'll be using shortly when we load the GLTF scene textures. If you're enjoying this video so far and want more of this content, please consider liking and subscribing to the channel. This really helps with the algorithm and makes all the hours of recording and editing that much more worth it. You can also support me using my Ko-fi link, which is in the description. Now let's get back to the lesson. The process of using a texture during rendering involves looking up a color or value inside of an image using normalized coordinates called UV or texture coordinates. This process is called sampling. We almost never use absolute coordinates since textures have varying dimensions. For this reason, UV coordinates are normalized from 0 to 1 for each axis, where 0 represents one edge of the image and 1 represents the opposite edge. The U coordinate is for the horizontal axis and V is for the vertical. When we use a sampler to retrieve a value from an image, or as it's called a texel from a texture, the texel is retrieved by sampling the image at the specified position using a filtering algorithm. There are two filters that can be configured for a sampler, the magnification and minification filters. These two let us control how we want to sample the image depending on how it's being scaled in order to texture the fragments on screen. If an image has to be scaled up, like in the case where we're looking at an object close to the camera, we're using the magnification filter. If the image has to be scaled down, then we're using the minification filter. The three filters in Vulkan are nearest neighbor, linear, and cubic. Nearest neighbor will snap to the current texel at the given UV coordinates and simply return that value for the color. Linear filtering will look at the neighbors around the UV coordinate and perform a linear interpolation along each axis, using the proximity of the texels to the UV coordinate for the interpolation weight. Cubic filtering works the same way, except it uses cubic interpolation instead of linear. In order to create a sampler with Vulkan, first we create an object of type VkSamplerCreateInfo. This is where we specify the magnification and minification filters we just talked about, as well as the address or wrapping modes to be used. As I mentioned, UV coordinates have a standard range from 0 to 1, representing the image texture in its entirety along each axis. That being said, there's nothing stopping us from providing UV coordinates that are, say, 0 to 2 or 10. We can scale our UVs however we want when we model our geometry to achieve all kinds of effects. When using UVs outside of the standard range, we can configure our sampler to perform different things to achieve various effects. The most common of these are repeating, where the texture simply repeats as our UVs exit the 0 to 1 range. We can mirror, where the texture once again repeats but does so in an alternating mirrored fashion. We can have the sampler clamp to the edge color of the texture and continue indefinitely. Or we can set a custom color and have a border generated when we exit the 0 to 1 range. The way we control these settings is via the address mode fields here. As you might have guessed, the U and V fields control how the texture is wrapped along the horizontal and vertical axes. The W field is for 3D textures and works the same way but along the texture volume's third dimension. Again, we'll look at 3D textures in the future. For our first sampler, we're creating a dedicated one for the fallback texture. It's using nearest neighbor filtering since we don't need any texel interpolations as we're dealing with a single pixel. For the address modes, we're using the repeat mode across all three axes. The compare enable field will be set to false here, but we'll come back to it when we cover lighting and shadows. To create the sampler, call VkCreateSampler, passing the address of the createInfo struct, no allocator callback, and the address of the vkSampler variable to receive the new sampler handle. The same way we generated an image ID for the GPU image resource, we'll push our new sampler into the application samplers vector and generate an ID for it. Now that we have the fallback image and sampler IDs, we can create a texture object in our application, which bundles them together. Later on, we'll be sending all of our texture objects into the fragment shader and use them in a method referred to as Bindless textures, a technique that allows us to draw many objects with many different textures without having to constantly bind them before rendering, as we had to do with older APIs. We've covered quite a bit already. We're able to create images, buffers, and samplers, which are basically everything we'll need to get the GLTF scene loaded. So let's start doing that. The first thing you'll notice is the call to the load_glTF method. This method takes a GLTF file path as a parameter and begins the import process. Inside this method, we get our first look at the TinyGLTF library API. Before we begin the import process, we can use the C++ file system library to ensure the file actually exists. If the file doesn't exist, we can just log an error and return out of the method. If the file does exist, we can proceed in parsing it. First, we need to create objects for the TG3 model, parser options, and errors. We also need to initialize the parser and error objects to ensure that there's no junk memory being used. Calling the respective init method and passing the address of each object is all we need. The next line is what actually parses the GLTF JSON and stores the results in our objects. This function takes the address of the model, errors, and parser options, as well as the file path as a C string and its length. When the parser is done, we need to check if everything went well by ensuring a TG3 OK was returned. If we didn't get an OK result, we can loop over the errors and log them. Before returning out of the method, we would also need to free the errors object to ensure any memory allocated for the error strings is deallocated. Provided the model was successfully parsed, we can move on to the happy path. While the image loading is fresh in our brains, we'll get started on loading the textures that will be used in the scene. This process involves loading the image files from disk using STB Image, then uploading them into VRAM the exact same way we just did with our fallback image. GLTF models normally bundle all image assets along with the model, and then refer to them in the JSON using paths relative to the document. For this purpose, we'll once again use the file system library to get the parent path of the GLTF JSON, which we can then use to generate the image paths themselves. Once we've done that, we can call the load_images method, passing in the TG3 model and the image directory path. Before we go over this method, recall that GLTF keeps a list of all images used in the scene. The simplest thing for us to do is to iterate through that list and load every image ahead of time. Later, when a particular material says it's using an image at some index, we can just grab it accordingly. TinyGLTF tells us the number of items in every single list inside of the GLTF document, using matching fields ending with _count. To get the total image count, we can use the images_count field of the TG3 model, and then use that to presize our images vector. We then iterate over every image in the model and load it using STB Image. On every iteration, we index into our vector and grab the image object accordingly, which is where we're going to store our image data. First, we use the image directory path that we passed in, along with the image URI to get the absolute path of the image file. Then we can use the STB load function to actually load the image data into RAM. This function takes the file path as a C string, as well as pointers to variables to receive the width, height, and number of color channels in the loaded image. The final parameter tells STB Image how many color channels we want in the resulting image data, regardless of the image source. For simplicity, we'll make all images contain 4 color channels for RGBA. Once this function returns and the image is loaded, a pointer to the image memory is returned and stored in the image object's data field. When we finish iterating through all of the images in the GLTF doc, our matching vector will be filled with all of the image data we need to move forward. In the end of load images, the vector is moved out of this function and received by the calling code. The next step is to get the images from RAM into VRAM. We've already seen the steps involved here, so we're going to look at this at a more high level. Let's hop inside of upload images. This method takes in our vector of image objects, uploads them to the GPU, and returns a matching vector with the new corresponding image IDs. We begin by creating a transient command buffer where we can record all of the GPU commands needed to copy the image data and perform the appropriate layout transitions. We'll also need a vector of GPU buffer objects. These will be the staging buffers we'll need to get the data from system RAM into the GPU's video memory. This vector will be sized based on the number of images we loaded from the GLTF file. Let's also create another vector of unsigned integers which will hold the newly created image IDs corresponding to the GLTF images. Now we can iterate over all of the image objects and record the required commands. First, we grab a reference to the image object, which will tell us the dimensions and number of color channels, as well as the pointer to the image data that we received from STB Image. If the image data pointer is valid, we can move on to copying. Otherwise, we'll just use the fallback image ID here and move on. To create the Vulkan image and copy the data, the steps are identical as before. We call createImage and pass the pointer to the image data, width and height fields, and the number of color channels. As we saw earlier in the video, createImage will create the vkImage, as well as the corresponding vkImage view. Then it will transition the image layout to transfer destination optimal, which is needed to copy the data into it. In order to stage the data, it'll calculate the image size in bytes and create a mappable vkBuffer in host memory, which is system RAM, so that it can then memcpy the bytes into it. Once the staging buffer is prepared, the vkCmdCopyBufferToImage will be recorded into the command buffer, which will perform the actual copy operation later on. The copy command engages the GPU's DMA hardware and streams the image data from system RAM into video RAM over the PCI Express bus. Right after the copy command, another pipeline barrier is recorded, which transitions the image layout to shader read-only optimal. This way, we leave the image in a state where it can be used in shader sampling operations. Finally, the newly created image ID and staging buffer are returned to the caller. Once we're back inside of Upload Images, we store the new image ID in our image IDs vector and push the new staging buffer into the staging buffers vector. This process continues until we've iterated over all of the STB loaded images. After the loop, the submit transient command buffer method is called with our command buffer, where the command buffer is ended, submitted to the graphics queue, waited on to ensure all the copy commands complete, and at the end is freed. At this point, all of the images have been uploaded to the GPU and the corresponding image IDs have been created to match. It's just a matter of iterating over the staging buffers we created for this process and freeing them, making sure we clean up after ourselves. Returning the image IDs vector now will move it out of this method and it will be received in the calling loadGLTF method. Since we cleaned up the staging buffers, let's not forget to also free the memory that STB Image allocated when it loaded the images from disk. This is done by iterating over the image objects and calling STBI Image Free on the data pointer inside each image. And with this, we're done loading the actual images and we can move on to the samplers. Earlier in the video, we covered the need for samplers and looked at how to create one. In this section, we can go over the specifics of how GLTF provides sampler parameters and how we can use those to create their Vulkan equivalents. The loadSamplers method takes in the TG3 model object and returns another vector of integers representing the IDs that correspond to the GLTF list of samplers. This time we use the model's samplers count field to size the vector and then iterate over the TG3 samplers. For each sampler object in the model, we have to convert between the properties in the GLTF document into the enum values that Vulkan can understand. We leverage static maps here that we can directly look into and get the Vulkan equivalent for whatever GLTF value we're converting from. In order to understand the mappings, we have to first talk a little about how the mag and min filters work in the context of mip mapping. First off, we aren't enabling mip mapping today, but we'll make sure the GLTF to Vulkan mappings here correctly interpret the configurations the GLTF spec expects. Mip mapping is a technique where we take our original texture image and create a chain of smaller images from it, each image in the chain being a quarter of the size of the image preceding it, all the way until we reach an image that's 1 by 1. During rasterization, the GPU can look at a cluster of fragments and the rate at which their UV coordinates are changing to decide whether the magnification or minification filter is appropriate. If the UVs are changing quickly in a small area of the screen, then we're using more of the texture but within a small section of the screen. This means we'd need the minification filter. And if mip mapping is enabled, the appropriate MIP level must be calculated for the texture to screen space ratio. As I mentioned, MIP level 0 is the original base level, and levels 1, 2, 3, and so on are the progressively smaller MIP images. MIP levels can also be fractional. If a MIP level is calculated to be 1.5, Vulkan can use a single MIP level or interpolate between two different levels. This is where the MIPMAP mode comes in. If nearest mode is used, Vulkan rounds to the nearest whole integer. 1.2 would become a 1, but 1.5 would become a 2. This is how the MIP level is selected. Linear mode uses linear interpolation, where the fractional portion is used as the weight between the two MIP levels. 1.2 would use MIP levels 1 and 2, but lean towards level 1. For the magnification filter, we generally always use the base MIP level. This is the largest image in the MIP chain and is obviously the highest resolution. The GLTF specification defines a series of filter modes that make inherent assumptions about how MIP mapping should apply in the context of minification. For this reason, our filter mapping needs to carry some extra information in order for us to ensure that minification is handled according to spec. The nearest and linear filter modes simply set the appropriate Vulkan filter equivalent directly, but they are non-MIP mapping modes, so we need to ensure they don't use lower resolution MIP maps during sampling, regardless of whether or not the image itself already has MIP maps generated for it. The rest of the GLTF filter modes are the ones normally used with MIP mapping, which is also evident by their names. What this means is that for the first two filter types, we need to be able to set the mag and min filters independently while making sure the sampler doesn't try to use any of the higher MIP levels, regardless of whether or not they exist. The filter map uses the TinyGLTF filter mode as its key, and a tuple as its value. The tuple values are the Vulkan equivalent of the filter, the MIP map mode we want to use for the filter type, and a float controlling the maximum MIP level allowed for this sampler. If MIP maps are to be ignored, you'd think that a maximum MIP level of 0 would be fine here. But if we did that, Vulkan would only ever use the magnification filter. This is because the hardware itself would branch to circuitry that has no concept of minification filtering and only ever uses the magnification filter. Instead of using 0, if we use a value of 0.25 along with a MIP map mode of nearest neighbor, Vulkan keeps the minification filter enabled while only ever looking at MIP level 0. This is because with MIP map mode of nearest neighbor, 0.25 gets rounded down to 0, effectively ignoring higher MIP levels. Put simply, this little trick allows us to create samplers with magnification and minification filters that are different from one another, while making sure that only MIP level 0 is used during sampling. This type of sampler can be useful when a MIP map enabled texture needs to be used in a context where it should only ever be sampled at its highest resolution, such as for UI rendering. For the rest of the sampler configurations, we use the VkLOD clamp none flag, which allows any number of MIP levels to be used. The second map is much simpler and simply maps between GLTF and Vulkan wrapping or address modes. Now that I've explained the mappings, let's take a look at how the sampler is created. Once again, we see the vkSampler create info struct. We already discussed what the filtering and address modes do earlier in the video when we created the Fallback texture sampler. All we need to understand here is how the GLTF mapping is used to create the Vulkan sampler. As you can see, for the mag and min filters, we first check if there's a filter specified at all. TinyGLTF uses the value of -1 to specify null values. So if there's no filter specified, we just default to the linear filtering for both. If there is a filter specified, we use the mag or min filter fields to look up the tuple from our filter map. Then we use the std get function and specify the index of the tuple value we'd like to retrieve. The first value in the tuple is the Vulkan filter mode, so we use index 0 to retrieve it. To get the correct minification filtering, we grab the MIP map mode from the tuple using an index 1 to get the appropriate tuple value. The wrapping modes are very straightforward. We just key into the map using the TinyGLTF define and get back the Vulkan equivalent. For address mode W, we can just default to repeat mode since we don't care about 3D textures yet. As I mentioned, min LOD and max LOD control the MIP levels allowed for the sampler. The min is always 0, but the max is set based on the last value in the filter map tuples, for the reason we discussed previously. And just like before, we can now call vkSampler create with the sampler create info object and get back the vkSampler object that Vulkan creates for us. If everything goes well, we push the sampler into the global sampler vector and get its corresponding integer ID. We then write this integer into our list of sampler IDs into the location of its corresponding GLTF sampler. If there was an issue creating the sampler, we log an appropriate error and use the sampler that we created for the fallback texture earlier in the video. Once we're done here, we can move the vector out and we have a list of sampler IDs corresponding to the GLTF model's sampler list. You'll recall from earlier that GLTF's textures are actually just groupings between an image source and the appropriate sampler that should be used for that image. Well, now we have the images loaded into VRAM and the samplers created as per the GLTF file. We can just hand our image and sampler ID lists to the loadTextures method, and it'll create the texture objects that we can use with our materials. Inside this method, we get our first glimpse of how easy it is to map between GLTF list indices and the global IDs that we've been generating for images and samplers so far. Since our current lists map one-to-one in size and order with the lists inside of the GLTF model, when the GLTF texture here says it wants an image or sampler at a particular index, we just grab the global ID out of the lists we passed in. Remember, these lists are just for the current model being loaded. The global lists are inside the application instance and will hold the loaded assets for any number of GLTF documents. All we're doing is generating IDs and mapping the GLTF indices to the global IDs that we're creating. This makes our texture creation pretty easy. First off, we'll check if we have enough room to add more textures into the renderer. The reason for this limit is that we'll need to send these textures over to the shaders using something called Descriptors and utilize a method called Bindless textures. We'll give Vulkan a big list of textures, and every material in the scene can just index into that list and grab whatever texture it needs during shading. This is how modern renderers handle textures. It completely avoids the overhead of binding textures all the time, which is usually a trip through the driver. And it also reduces the need to group draw calls together simply based on what textures they're using. The max textures constant is set at 1024 textures and is plenty for our purposes, but that can easily be bumped up higher by simply changing the constant. We'll even make this dynamic when we take our asset loading to the next level and create a full asset pipeline in the future. Right now though, we need to get our textures created so we can send them to the shaders later in the video. Once again, we create a vector to hold our texture IDs and base its size on the texture count in the GLTF model. As we iterate over the TG3 textures, all we do is push a newly created texture object and use the indices specified by the TG3 texture to look up their corresponding IDs in the vectors that we passed in. After pushing the texture into the vector, we use its size to get ourselves a texture ID and write it into the texture IDs list. We can then just return and move this list back out and head back over to the load GLTF method. Up next, we load the GLTF materials. For that, we needed the textures loaded, so when we call load materials, we pass in our new texture IDs list. The concept here is the same as what we just did. Each GLTF material will use a texture index to refer to its texture maps, and we'll use those indices to figure out what texture ID that corresponds to in our renderer. I'm assuming you're getting the hang of this by now. We create a vector of material IDs, size it according to the materials list in the GLTF file, and iterate over the TG3 materials in the model. As I mentioned at the start of the video, the GLTF spec can represent some very complex PBR materials, which we'll dive into in a later video. For the materials today, we want to know what the base color of the material is, as well as any base color texture map required for shading. For the base color, we can read it out of the PBR metallic roughness object, where it's stored in an array of 4 doubles called base color factor. This represents the RGBA values we use when shading objects with this material. Next, we check if the TG3 material has an associated base color texture by checking if the base color texture's index field is a valid GLTF texture index. This texture is often called the albedo map or the diffuse map. If a valid index is provided, we can grab the texture ID corresponding to it from our texture IDs vector. For the materials though, we want to convert our texture ID into a valid texture index. Since we have a very simple ID scheme, we only need to subtract a 1 from each ID for it to become an index. We do this because we want materials to directly index into the textures list later in the shader. Any material without a texture here gets a texture index of 0, which, as you'll recall, is the first texture we created, which happens to be the 1x1 pixel fallback texture. With this setup, our samplers can just sample directly using the material's texture index and never have to worry about whether a material has a base color texture or not. It'll either be a real texture or the fallback texture. Once we fill our vector of material IDs, we can return that out as well and head back to the load GLTF method. With the materials ready to be used, we can load the meshes and link the appropriate material IDs now. Once again, we begin by pre-sizing a vector to hold the IDs we'll be generating. In this case, these will be the global mesh IDs. The TG3 model exposes the meshes list along with its size via the meshes count field. For each iteration over the TG3 meshes, we'll first create an instance of our own mesh struct to hold the data that we read in. This struct is basically a container around submesh objects. Submeshes, or primitives as they're called in GLTF, are the actual renderable geometry in the scene. I'm personally not a fan of the term primitive here, as it already has an established meaning in programming and isn't as descriptive as submesh, I think. Name aside though, the point of the submesh or primitive objects is to specify the number of vertices, indices, and material to be used during rendering. After creating our mesh object and grabbing the TG3 mesh, we can begin by copying over the TG3 mesh name into our own mesh object. This will be useful if we need to debug things. In order to make sense of how we load the data, let's revisit the GLTF reference guide and chat about buffers. All the geometry in GLTF resides in binary files referred to as buffers, which sit alongside the JSON file and need to be loaded separately. TinyGLTF loads them for us and provides pointers to their memory, so this is pretty easy. All we have to do is just read from them correctly. Each buffer entry in the JSON will have its size and associated file URI provided. To make sense of the data inside a buffer, we need to read it according to its buffer views. Each buffer view looks at a particular buffer and specifies an offset to read from, along with the size in bytes. There's also a byte stride, which tells us how many bytes to move forward by each time we read a piece of data. Beyond buffer views, there are also accessors, which directly describe how a vertex attribute should be read from a buffer view. They further offset into the buffer view and tell us the type of data we actually need to read. In order to store the mesh data, we'll use a vertex struct that will hold the attributes we're interested in for every vertex in the scene. This includes the vertex position, color, normal, and UV coordinate. The position and color are pretty self-explanatory. The normals tell us the direction a surface is facing and will be used for lighting calculations later. The UVs are the texture coordinates we'll be using during sampling operations. Each of these pieces of data are referred to as attributes in GLTF, and we have to read them individually as described by their accessor. Each primitive has a list of attributes, and we'll be looping over them and finding the attributes we're interested in, and then reading the data into our own vertex structure. To avoid repeating the same code for every attribute we read, we can use this lambda here and just call it repeatedly. This is a C++20 templated lambda, which figures out what type of data to read based on the vertex field we're writing to. Its first parameter is a pointer to a vertex structure member field, and the second is the GLTF attribute we're reading. When we read a particular attribute, we first look up its corresponding accessor. The accessor tells us which buffer view we should be using to read the data, and of course, in turn, which buffer the data is actually in. Armed with these objects, we can calculate the data offset to start reading from by summing the buffer view and accessor offsets together. The buffer view stride field is also taken into account, and we need to check if it's non-zero before using it. If it is 0, we just use the size of our template parameter instead, which will be either a vector 3 or a vector 2. Next, we can start iterating over the attributes data and writing it into our global vertex buffer. Every element's memory address is calculated by adding the product of the current index and stride to the buffer offset we calculated above. We can then cast this memory address to a float pointer and access the values directly. For those that aren't familiar with if_const_expr, it gets evaluated at compile time, so there is no runtime branching here. Each path is compiled separately depending on the types we call the lambda with. Inside the if blocks, we index into our global vertex buffer, using a global write offset and the current element index. You'll recall that we pre-allocated a global vertex and index buffer at the start of the video. Here we finally get to use them. The way we write all the vertex data is as follows. When we start processing a GLTF primitive, we write each vertex starting at the current global offset position, and write each vertex in sequence. When we finish with that primitive, the global vertex offset is moved forward by the number of vertices written, and the next primitive's vertex data is written immediately after it. This exact same approach is used for the vertex indices, which we'll look at shortly. This also means that when we render, we don't have to constantly switch between different vertex and index buffers for different meshes. That would add significant overhead. All that's needed here is for us to specify where in the vertex and index buffers we're reading from, and the appropriate mesh data can be retrieved. To write the attribute data, we index into the vertex buffer and then address the appropriate field using the member pointer we received. Depending on the data type of the member field, a vector 3 or vector 2 is created, and the values are read directly using the data pointer we calculated above and some simple indexing. This lambda will get called repeatedly for every attribute we're interested in and for every primitive in the scene. Since we have the tg3 mesh object, we can get the primitives count from it and resize our mesh's submesh vector to match. For every primitive, we first need to map its GLTF material index to one of our very own material IDs that we created earlier. This is a simple matter of indexing into the material IDs list, grabbing the resulting ID, and storing it into our submesh object. We also set the submesh's vector start position by assigning it the current value of the global vertex offset. This is the offset where we're about to write our vertex data, and is therefore the start of this submesh's vector data. Now we can loop over the primitive's attributes and grab each attribute as we go. These are just string and integer pairs that create a mapping between the attribute name and the accessor index it's associated with. Inside the loop here, we'll look for a certain number of attributes, starting with position. A simple string compare can be used between the attribute key and the attribute name we're looking for. Once we find the position attribute, the first thing we do is grab its accessor by using the attribute's integer value to index into the model's accessor list. And once we have the accessor, we're ready to read the data. Before we do that, we have a couple of asserts to make sure that 1, the data is what we expect it to be, a vector 3 made up of a series of floats, and that we can actually fit the vertices into our global vertex buffer. Next, we record the number of vertices making up this primitive object by writing the count value of the accessor into our submesh's vertex count field, since the number of positions are also the number of vertices overall. With these two fields, we'll know exactly what part of the vertex buffer contains our submesh's vertices. And now our first call to the write attribute lambda. We pass in the address of the vertex's position field, along with the position attribute we're currently looking at. This will execute the lambda, retrieve the accessor by index, its associated buffer view, and finally the buffer as described previously. Then we calculate where in the buffer the position data is according to the buffer view and accessor offsets. We figure out the appropriate stride, and iterate over the position data in order to read and then write a series of vector 3 objects into the position field of the corresponding vertices. This is how we get the vertex positions. To get the vertex color, normal, and UV coordinates, the process is the same. Find the appropriate attribute by name, make sure the type and component types are what we support, then call writeAttribute, passing the address of the corresponding member field and the attribute object itself. Something I'd like to point out is that we're looking for attributes color 0 and texture coord 0. The vast majority of mesh data has only one color and texture coordinate per vertex. There are certainly cases where multiple UV coordinates will exist per vertex, as that can be quite useful for things such as baking lighting. To keep the scope and complexity of this tutorial somewhat controlled, we're only looking at the first UV channel here, and you'll find basically every model that you load will likely work perfectly fine this way. That said though, each GLTF material's texture map also specifies the UV channel that we should be using when sampling, though in the vast majority of cases this will just be the first UV channel. In the future, we'll support multiple UV channels as it will become more important for various rendering features. After we've finished iterating all of the vertex attributes for the current GLTF primitive, we need to advance the vertex offset position so that the next primitive's data can be copied starting at the correct offset. The current primitive's vertex count is added to the vertex buffer offset, and the write head is moved forward to the new position. Up next, we'll need to load the vertex indices associated with the current primitive. In order to optimize memory use, each model usually has a list of indices along with the vertices. As we're all aware, we're rendering meshes using triangles, and adjacent triangles share vertices. Scale this up to a large mesh, and all of these repeated vertices add up fast. For this reason, we usually get a list of unique vertices in the mesh, as well as a list of indices laying out the order in which those vertices represent the mesh data. This way, when a vertex is repeated, we're only repeating its integer index rather than the entire vertex. Retrieving the indices is very similar to what we just did, except we don't have to look for any attributes. We just need to check that the indices accessor is provided by making sure its index is valid. Then we can grab the accessor, BufferView, and buffer and check if the global index buffer has enough space to store the data. If we're all good, then we can track the index start position for this primitive as well as the number of indices. Now, our index buffer is a series of 32-bit integers, so we need to make sure that all of the index data we write is represented this way. GLTF, on the other hand, doesn't always use 32-bit integers. It could also be 16-bit short ints. So we have to be careful about how we copy the data. In the case of 32-bit ints, we can simply just copy the data over by first calculating its start position in the buffer and casting it to a uint32 pointer. Then we can just use memcpy into the current index buffer's offset position from the pointer we just calculated. The size in bytes to copy is the accessor count multiplied by the size of a 32-bit integer. If the data is provided by 16-bit integers, we can't just copy it over since our internal data doesn't match what GLTF is providing. What we have to do is get the pointer to the index data as a 16-bit uint pointer, iterate over each one, and then cast each 16-bit integer into the 32-bit we're actually recording. Pretty simple in either case. Finally, the index buffer offset is incremented by the current index count so that the next primitive's indices can be written correctly. Once we've processed all of the primitives in the current TG3 mesh, the mesh object is moved into our application's meshes vector, and once again we use the size after push to generate the ID. In this case, this will be the mesh ID we'll be using during rendering. Once all of the meshes in the model are processed this way, we can just return the list of mesh IDs out, and we can move on to finalizing the GLTF loading process. We now have the mesh IDs we'll be needing to draw everything in the GLTF scene. The scenes themselves are composed of node objects, and the nodes may also have children of their own, forming a tree of nodes. Each node in the tree has its own local transformation relative to its parent. This means that when we render the scene, we'll have to make sure that each node we draw is also transformed by its parent. For our renderer and future game engine, nodes will be the core objects that we create. For today, we'll look at how to implement the node class along with the NodeWorld class, which is where all the node objects will live. We'll keep the implementation simple today. All we need to do is create nodes during loading, make sure we can connect them in the form of a tree, transform them into their scene positions, and assign them a mesh ID that they'll be drawn with. We can keep this simple since we're just loading and rendering a static scene. When we introduce elements that need to dynamically spawn new nodes or remove existing ones from the scene, as you'd find in a real game, we'll take this NodeWorld concept much further by turning it into a node pool. Nodes will be represented by generational IDs. We'll be able to remove and reuse nodes easily at runtime with the use of a free list. And the generational aspect will ensure that we can reuse the objects in the pool. The nodes are going to become the core game objects and will have components attached to them, which is how we're going to be able to compose together complex gameplay objects without relying on rigid class hierarchies. All of this in due time. For today, we just focus on the node hierarchy and rendering. Each node holds its transformations directly in the translation, scale, and rotation fields. Translation and scale, of course, use a vector 3, but the rotation is represented by a quaternion. Quaternions are an interesting topic which is better left for a math guru to explain in detail, of which there are plenty on YouTube. Quaternions are a good choice for representing rotations as they can represent any rotation, are easily interpolated between, which makes them great for animation, and they don't suffer from gimbal lock. Another way to represent rotations for an object is using Euler angles, where you simply specify the degrees by which you want to rotate an object along each of its axes. This approach is much more natural for user interfaces and direct manipulations, as quaternions are much harder for people to work with directly. Inconsistent ordering of Euler angle rotations, though, can result in gimbal lock, which is basically just a loss in a single axis of rotation. So normally the UI will express rotations using the 3 axes, and then convert those rotations to a quaternion behind the scenes and store it that way. Before we can render a node, we need to first compute its transformation matrix based on the 3 fields we just discussed. This involves producing a matrix from each one, then multiplying them together to get the local transformation matrix for this node. Since this involves some number crunching, we introduce a simple optimization that only computes the transformation matrix if one of the transformation fields has been changed. To do this, we use the dirty flag seen here. The setter for each of the transformation fields sets the value of the corresponding field and then sets the dirty flag to true. Looking again at the getTransform method, we'll see that the matrix is actually only ever computed when this flag is set to true. In which case, each field is turned into a 4x4 matrix, the new transform matrix is computed and then cached in the node, after which the dirty flag is set back to false. Subsequent calls to getTransform would see a false here and simply return the cached matrix, rather than recomputing it from scratch each frame. The translation and scaling matrices are simple calls to the glm translate and scale functions. The rotation matrix can be obtained using the mat4cast function. And to get the local transformation matrix, we multiply the matrices in the following order. The multiplication order here is important because when we end up multiplying vertices by this matrix, the order of operations will be right to left. This results in vertices being first scaled, then rotated, and finally translated. Rotation and scaling always happen around the object's origin, so if we translated the object first and then rotated and scaled, the rotations would turn into orbits and the scaling would also look off. In some cases, GLTF gives us the transformation matrix directly, rather than separate fields for translation, rotation, and scaling. In this case, we call our setTransform function, which decomposes the matrix down to translation, rotation, and scaling fields, and then stores the matrix directly. Since we're just storing the matrix, we can also set the dirty flag here to false. Now, to express the node hierarchy, we'll be using something called an intrusive tree structure. All this means is that every node in the tree stores direct links to its first child and next sibling nodes, and we'll also link up each parent node this way as well. This approach is great as it doesn't require any dynamic memory to represent a node's children. This means that we can easily store all the nodes in a contiguous list, and as we'll see in the future, pool and reuse them. When we want to traverse a node's hierarchy, we just simply follow the first child link, and then follow each child's next sibling link, until we reach a next sibling of 0 or null. To store all of the nodes, we can create something like this NodeWorld class. It's responsible for creating new nodes and retrieving existing ones using their ID. As I mentioned, since our nodes are all the same size, we can easily store them in a pre-sized vector or array. The initialize method here calls the vector's reserve method with the maximum number of nodes that we can hold, and we call it inside the application's initialize method. This means that we never allocate new memory for nodes at runtime. We just have to make sure that we have enough space for the scenes we're loading up front. That's all we need for now. If you run into a situation where you run out of nodes for a particularly large scene, just bump up the maximum here. The create node method has an assert that checks if we still have space before adding a new node. Then just pushes a blank node into the vector, generating a simple integer ID, just like we've done with everything else so far. The method then returns a pair containing a reference to the new node, as well as its ID. This way we can start using the object and ID immediately at the call site. Once we start adding and deleting nodes dynamically at runtime, we'll switch this over to a node pool, where we'll be able to remove and reuse node objects at runtime. Each node ID will turn into a node handle structure containing two integers, one for its integer ID and another for the object's generational ID. Each time we reuse a node in the pool, its generational ID will be incremented. This helps us avoid incorrectly referencing a dangling node ID that has been recycled, but more on this very soon. For today's job, what we have here is perfectly sufficient. The getNode method just takes a node ID, makes sure it's not 0, which represents null in our world, and then indexes into the node's vector and returns a reference to the object. You'll recall that our IDs are just the index plus 1, so retrieving the object is very trivial. One final note on nodes is to be sure to initialize the transformation fields as follows. We use all zeros for translation, which defaults objects to the origin. The scale is set to all ones, which keeps a one-to-one scaling across all three axes. The rotation quaternion is initialized with the values w, x, y, and z, and we need to ensure that the w is initialized to a 1. This is because the w component is tied to the cosine of the angle of rotation, so a value of 1 just means no rotation. You should now have a solid understanding of how we're representing the nodes in our renderer. We can now take a look at how GLTF represents nodes and how to load them from the scene. Scenes in GLTF are nothing more than a list of node indices. These are the root nodes in the scene. What we'll do is recursively look at each node, traversing its child nodes, until we've visited every single node in the GLTF scene. First, we need to grab the scene from TinyGLTF. There's often a default scene value set. If this is a valid index, we can use it to directly grab the scene object from the TG3 model. Otherwise, we'll just default to the first scene at index 0. Once we have the scene, we can iterate over its root nodes, which are stored in the scenes nodes array. For each root node, we'll call our import node method, which imports the GLTF node into our renderer, and also recursively imports all of its child nodes. This method returns the ID representing the new node object, which we can use to link nodes together. The best way to understand the node import process is to jump right into the import node method and step through it. Then we'll come back here. As we iterate and import each GLTF node, we pass in its index into this method via a 32-bit node index parameter. This lets us begin the process here by grabbing the TG3 node from the model's node list. Next, we create a node of our own in the NodeWorld, which gives us our node object and its new ID. One of the parameters of this method is the parent ID of the current node we're creating, so we can just set that directly on our new object. Next, we can process the GLTF node's transformations. As I mentioned earlier, the node can directly specify its matrix, or split the transformation across the translation, rotation, and scale fields. In the case where we're given a matrix directly, we'll create a new 4x4 matrix and get a pointer to its data using the value pointer function. After that, it's a simple matter of iterating over the 16 values making up the matrix and copying them over, making sure we cast the doubles that come in from TinyGLTF to floats. Once the matrix values are loaded, we can call the setTransform method we saw earlier, which decomposes the matrix into translation, rotation, and scale parts and caches the matrix. If the GLTF node's transformation is provided as separate fields, we can load them directly and store them in the node. Please note that GLTF provides the quaternion components in the order X, Y, Z, then W, and our GLM quaternion expects W, X, Y, Z. Then the transformation field setters are called, and we can move on. Next, we check if the GLTF node has a valid mesh index. If so, we can use it to grab its corresponding global mesh ID from the mesh IDs vector that we passed in. Some nodes won't have a mesh and will simply be used to group objects together in order to transform them as one. The next block of code is what ensures that sibling nodes are linked together. Since the import node method is what creates new nodes for us from GLTF, we'll pass in the ID of the previous node we created prior to this one so that its next sibling ID link can be set to the new node we just created. This involves grabbing the node from the NodeWorld using the previous sibling ID, but only if it's non-zero. Then we just set the next sibling ID to the node ID we just got. This way, the two siblings are now connected and can be traversed during rendering. Don't forget that this method is also used recursively across the entire GLTF node tree, so we need to iterate the current TG3 node's children and call it again for each one. Let's go over the data we're passing to it. First, we pass in the NodeWorld. This parameter didn't need to exist as import node is an instance method, but this wasn't the case originally and I forgot to remove the parameter, so whatever. Next is the TG3 model, which we'll need to read the scene data. After that is the index of the TG3 node that will be imported, which I've explicitly stored in this variable here. The next field specifies the parent ID that will be associated with the newly created child node, which is of course being set to our current node ID that we created above. The next field is the ID of any previously created node in the chain. Notice the unsigned integer declared outside the loop that is being initialized to 0. As we iterate and create child nodes here, we keep track of the last node ID that we create. This value is then passed in as the previous node ID argument, which as you saw earlier is used to look up the previous node and set its next sibling ID field, creating the chain of sibling nodes. And of course, we're passing along the mesh IDs list, which our loadMeshes method created. It's also important for us to make sure that the first child node is set appropriately. This is easily done using the following block of code. During the first iteration of this loop, the first child ID field of our node will still have its initial value of 0. In this case, the last child ID, which holds the ID of the child node that was just created above, will be written to the first child ID field of our node. Subsequent iterations will see that the first child ID is no longer 0 and simply skip this block. So, to recap, the linking works as follows. Our new node is created here, and that gives us the node and its ID. Then the parent ID of our new node is set according to the parent ID argument passed into the method. Next, we make sure that this node's previous sibling has its next sibling ID field pointed to our new node here. Then the node's children are also created. Our node's ID is passed in as their parent. Each previous child's ID is tracked so that we can look it up and set up the next sibling links, and the parent node has its first child link set. At the end of this method, the node ID is returned to the caller, and each recursive call to import node is popped off the call stack. I highly recommend being comfortable with recursive programming in order to fully make sense of what we're doing here. Hopefully seeing this method first was helpful, so you can now easily understand how we can load the scene's root nodes as well. As we iterate over the scene's root nodes, we call the import node method and pass the GLTF node's index so that we can import it into our renderer. This time we're passing 0 for the parent ID since it's a root node. Next, we use the last root node ID field as the previous node ID argument, which will require some explanation. At this point, you'll probably see how each node pointing to its next sibling essentially forms a linked list. And linked lists generally track their head, which is the first node of the list, and their tail, which is the tail end of the list. The last root node ID field tracks the tail of the list, which is how we know where to connect any newly created root nodes. This is the reason why it's passed in for the previous node ID parameter. As you just saw, the import node method will look up the node with this ID and make sure its next sibling field is set to the ID of the new node that it creates. Then once we get the new node ID here, we make that one the new tail by storing its ID in the last root node ID field. The root node ID field serves the opposite purpose. It's the head of the list. The first node we create has its ID tracked by this field, and any subsequent nodes simply become the tail. Once we're out of this loop, we've officially loaded everything we wanted from the GLTF model for now. We can also safely free any memory allocated for it by TinyGLTF using the tg3 model free function. And then we can head back over to the load data method. You should now have a good understanding of how all of the resources are loaded, as well as how scene nodes are managed in our setup. Many of the models you'll download, especially from Sketchfab, will have a single root node that is mainly used to transform the entire scene. Importing the GLTF into Blender would let you see that clearly. If you wanted to transform this node in our renderer, you could easily retrieve it from the NodeWorld using the root node ID we discussed and set its transformations directly. The Mario Kart model I was playing with was quite large, so I scaled it down to 1/100th of its original size and translated it down 5 units along the y-axis. As we'll see shortly, when we render, this top node's transformation matrix will get propagated to all of its child nodes, affecting everything below it. So after the call to load GLTF, we can finalize the loading process. The geometry data is still just in our global vertex and index buffers, so we have to upload it to the GPU. The texture data is already in video memory, so all that's left to do there is tell the shaders about it. And finally, the materials will be uploaded to the GPU as well and exposed to our shaders. We can start by staging the geometry data so that we can copy it to the GPU. We've seen how most of this is done earlier in the video, so I won't spend too much time repeating things. To upload the mesh data, we'll need to create a few buffers. We'll need 2 staging buffers as well as 2 device local or video memory buffers, which will be the final destination for the vertex and index data. Starting with the vertex staging buffer, we once again call the createBuffer method and specify the buffer usage transfer source flag. The vertex buffer size in bytes will just be the global buffer size we calculated initially. We could have also just calculated the exact size in bytes based on the number of vertices we copied, rather than just using the total allowed size. But this is simpler for now, you can change that if you'd like. Passing a true argument here is what flags this buffer as mappable. And the VMA flag here tells VMA to make the appropriate decision on where this memory should be allocated from. Let's take a brief look at this method again. The buffer usage transfer source flag is used by the vkBuffer create info struct here, as well as the size we provided. The VMA auto flag is copied here, and since we're requesting a mappable buffer, the create host access sequential write bit is also applied, stating that we want to write to this buffer sequentially from the CPU. Then the buffer is created, once again without the shader device address section being executed. We'll come back to this in a second. And with that, we have the Vertex staging buffer. Creating the index buffer is identical, except of course for the size, so we can just move past it. Next step is to create the device local buffers that our GPU will read from during rendering. Once again, we call create buffer, but this time with different arguments, starting with the Vertex buffer usage flags. We want this buffer to be a transfer destination since we'll be copying to it from the staging buffer. This time though, we're adding the shader device address bit here, which will let us retrieve the address of the buffer's memory and read vertices from it directly in the Vertex shader. This is called Vertex pulling, and it's a modern technique to completely bypass the input assembly stage of the graphics pipeline. It removes the need to configure input layouts, deal with binding limits, and it opens the door to other advanced geometry management techniques. With the shader device address bit set, the create buffer method will now execute this block that we've been ignoring. It fills in the vkDeviceAddressInfo object, specifying the handle of our newly created buffer, and then gets the memory address of this buffer by calling vkGetBufferDeviceAddress. Once we have the address, we write it into our GPU buffer structure's device address field so that we can later hand it to the shaders. This field is simply a 64-bit integer. Remember that in order to use BDA or buffer device address, you should enable it during device creation. First ensure that it's actually supported. Then ask for it to be enabled using the Vulkan 1.2 feature struct. Device creation was covered in the first video of the series, so be sure to visit or revisit that if you have any trouble here. Once this call completes, we'll have our Vertex buffer. Since we're not asking for this buffer to be mappable and host visible, VMA will automatically allocate it for us in device local memory. Note that for a Vertex buffer, you normally need to include the VkBufferUsage Vertex buffer bit, but since we're using Vertex pulling and bypassing the standard Vertex input assembly stage, this isn't required here. The index buffer, on the other hand, is pretty standard. It requires the VkBufferUsage index buffer bit since it will be used as such during rendering, as well as the transfer destination bit so that we can copy into it. All calls to create buffer return for us GPU buffer objects containing the vkBuffer and VMA allocation data. Since we only used it for staging buffers so far, which we freed immediately after use, we didn't need to keep track of them for later. For our Vertex and index buffers, we'll hang on to them until the application terminates inside of the application's GPU buffers vector. This is what the addBuffer method does. The GPU buffer is pushed into the buffers vector of our application, and returns a buffer ID integer for us, just like how we've done with every other resource so far. This will become more and more useful as our need to manage more and more buffers grows. Our global Vertex and index buffers will be tracked and we'll hang on to their IDs. Now we can use the memcpy method yet again to copy the Vertex and index data from our vectors into the staging buffers. We'll pass in a reference to our Vertex staging buffer first, 0 for the write offset, and the data pointer of the Vertex data vector, and once again the total number of bytes of the buffer. Just like we saw earlier in the video, the buffer's memory is mapped and we get a pointer directly to it. Then we can use memcpy to get the data from the Vertex vector into the staging buffer's memory. Once we're done copying, we can unmap the memory and continue on. The index buffer is copied in the exact same way, so we can skip the explanation here. We're of course changing the buffer handle and the size here. Now that our buffers are ready, we can perform the copy from staging into the device local buffers. We get our transient command buffer by calling start transient command buffer, then schedule 2 copy commands, one for the Vertex data and one for the index data. The vkBuffer copy objects are created, specifying a 0 for the source and destination offsets for the entire buffers, along with the actual size of the copy operation. Then we call vkCmdCopyBuffer with the source and destination buffers and the addresses of the vkBuffer copy objects. Then it's just a matter of submitting and waiting on the command buffer to complete, and we can move on to cleaning up. Here the Vertex and index staging buffers are destroyed, their memory is freed, leaving us only with the final device local buffers. At this point now, we've uploaded our Vertex and texture data to the GPU, which means we're pretty close to being able to render it. Before our texture data can be used by shaders though, we need to actually tell Vulkan how we want to expose the data to the shaders. You'll recall I said we'll be using a technique called bindless textures. Traditionally, we've had to constantly change the texture binding state during rendering in order to ensure the right textures are in place so that the fragment shader can sample them. This change of state is pretty taxing as it requires a full round trip through the graphics driver in order to change the texture binding. To mitigate this, graphics devs would group objects based on what materials and textures they were using in order to reduce the number of texture state changes they had to make throughout the course of a frame. This introduces some complexity and makes other techniques more difficult to implement. Nowadays with Vulkan and other modern APIs, we can simply just describe all of our textures and expose them in a big list for our shaders to index into. Also recall that our materials keep track of their required texture indices, which we'll be using in the shaders to retrieve and sample the textures. In order for us to describe all of our textures, we'll have to use something called descriptors and descriptor sets. Descriptors do exactly what it says on the package. They describe resources that we wish to use inside shaders. This can be images, samplers, and buffers, amongst other things. A descriptor set is like a mapping table, where the descriptors it contains map our resources into what the shader should expect. Resources exposed to a shader via a descriptor must be bound to a particular binding location. And of course, the shaders must know this location so that they can reach it and find the data that it describes. Binding locations are simply just indices within a descriptor set. This means that you can use the same binding location across multiple descriptor sets, since it's really just like an index within a particular descriptor set. Traditionally, descriptor sets were the go-to method of passing data to the shaders, that and push constants, which we'll see shortly. It was very common to create multiple descriptor sets where each set would correspond to a particular update frequency. For instance, you could have one set for global data, which would rarely be updated, then another set for a single frame, and maybe even another descriptor set for individual draw operations. As you can imagine, this can get pretty complicated and is often a major point of confusion when starting out. Nowadays, you'd be less inclined to use descriptor sets since we'll be using the BufferDeviceAddress features to get data into our shaders. But for bindless textures, we still need to use descriptors, though the setup is pretty simple and easy to understand. Let's start off by looking at how we actually update the descriptors themselves, which should make it easier to understand how they're designed to be used. Afterwards, we'll look at how to create the descriptor set and actually allocate the needed descriptors. Since we're near the end of the load data process, all the textures of our scene are already in the textures vector inside the application. This means that we can loop over our textures and write a descriptor entry for each one inside of our global descriptor set. This is precisely what the update texture descriptors method does. First, we create a vector of VkDescriptorImageInfo objects and reserve enough memory in it to describe all of our textures. Next, we simply loop over each of our texture objects and push into this vector a descriptor info object for each texture. Recall that our textures are a combination of an image and a sampler required to sample that image. The descriptor image info struct requires just that. We'll first grab the sampler handle using the sampler ID we stored in the corresponding texture object, and store it in the sampler field here. We'll then grab the texture's associated image using the texture's image ID, and store the corresponding image view in the descriptor's image view field. We'll also need to specify the layout that the image is currently in. Remember, we already transitioned all of the images into the shader read only optimal layout when we uploaded them to the GPU, so we'll set this layout here. After processing our entire textures vector, we'll have all of our descriptors prepared and ready to be written into the descriptor set. To do that, we'll need an object of type VkWriteDescriptorSet, which allows us to write descriptor set entries into different binding points in the descriptor set. To write our list of image descriptors, we'll need a single VkWriteDescriptorSet object with its binding location at index 0, specified in the destination binding field. At this binding location, we're describing a list of combined image and sampler descriptors. This is what the descriptor type field here specifies. The list size is set using the descriptor count field, and it simply receives the size of our image descriptors list above. The pImageInfo pointer receives the pointer to our image descriptors data, and the destination array element lets us specify which descriptor index we want to start writing from. This can let us perform partial updates of descriptors, which we won't be doing, so we'll just start from the beginning and specify 0 here. And of course, we need to specify the descriptor set that we're actually writing into. This is specified in the destination set field, which receives the handle of our global descriptor set. We'll look at how this descriptor set is created in just a second. To perform the actual update, we call VkUpdateDescriptorSets, along with the VkDevice, the number of descriptor write objects, of which we have just one, and a pointer to the descriptor write info object we just created. We're not using the last two fields here, but they're used to perform GPU-side copies of descriptors, which we're not interested in just yet, so we can specify a count of 0 and null pointer for the last parameter. At the end of this method, all of our textures will have corresponding descriptors written about them at binding location 0 in the global VkDescriptorSet. Now that we understand what goes in a descriptor set and how to populate it, let's actually create one. If we revisit the initialize Vulkan method, which we created in the last video, we'll see that there are a couple of new calls here. The one we're interested in now is the createDescriptorSets method. So let's drill down into that. When a descriptor set is created, it isn't directly allocated in place, but rather allocated out of a pool of memory we create ahead of time called a descriptor pool. I always found the need for a descriptor pool kind of odd, as you don't normally destroy and recreate descriptors on the fly, which is what pooling is normally used for. At most, you'll be updating their data pretty often. Pooling is a great tool when you need to recreate objects all the time, and don't want to constantly ask for new memory. This is why it's perfect for command buffer recording, for example. We constantly create and record new commands and command buffers, so command pools are excellent for this. So why do we need them for descriptors? To draw a comparison, in DirectX, descriptors are just slots inside of a heap. You ask for a chunk of memory to write your descriptors into, and then just increment pointers and write whatever you need into that heap. Quite a bit simpler than in Vulkan. But DirectX is tailored towards desktop GPUs and Xbox systems, not so much mobile devices. Vulkan, on the other hand, is a true multi-platform API which treats mobile GPUs as first-class citizens. And mobile GPUs, at least at the time of Vulkan's inception, couldn't just give you a descriptor heap, and emulating such a feature would have required some hairy driver programming. So while I personally prefer DirectX's approach to descriptors through simple heaps, among some other design choices as well, descriptor pooling was necessary to abstract away descriptor memory across all types of devices, and is a small price to pay for true cross-platform abstraction. Let's see how we can create a pool that can hold a whole bunch of texture descriptors. Each descriptor pool needs to know the types of objects it needs to allocate memory for. In our case, we only need space for a list of images. The VkDescriptor pool size array here is how we specify the types and number of things we want our pool to be able to allocate. So for the image list, we'll add a single VkDescriptor pool size object with a type combined image sampler and a descriptor count of max textures. Max textures is just a constant I've defined at the application level, which is the max number of texture descriptors we'll support for a given scene. Currently it's set to 1024, which is plenty for our current scenes, but it can be easily bumped up as needed. Next, we'll configure some things about the descriptor pool. First thing to discuss here is the flags field, which has a flag named UpdateAfterBindBit. This is very important, so let's look at it in a little more detail. When you specify this flag, it tells Vulkan that we're allowed to make updates to descriptor sets allocated from the spool even after they have been bound. But we also need to make sure that we don't update specific descriptors that are currently being used by the GPU. Which means that in our multi-frame in flight renderer, we could make updates to image descriptors on the fly, but we would have to be careful about which descriptors we update depending on which frame is currently being rendered. We won't be doing something like this yet, as our textures are updated just once at scene load time. So why are we even specifying this then? Traditionally, image descriptors in Vulkan are normally saved directly in some hardware registers, of which there is a limited number. This is why developers constantly have to juggle different textures in large scenes. When you specify the UpdateAfterBind flag, we're also telling Vulkan to record our image descriptors in a completely different large heap of memory, which allows us to expose a massive number of image descriptors to the shaders. This is how bindless textures become a possibility. With that said, there is a little bit of indirection happening here because of our descriptor indexing, but from a performance perspective, it's often non-existent thanks to caching, and certainly doesn't affect sampling performance at all, since it only relates to the actual indexing of the descriptors. On the flip side, we completely eliminate the CPU overhead of constantly binding different textures, and the complexity of grouping draw calls per material, leading to a definite net win for us in the performance department. And with that out of the way, next we specify the maximum number of descriptor sets that we can allocate using this pool. We specify one here for our single global descriptor set. Then we provide the list of size objects we just defined above, and call VkCreateDescriptorPool with the pool info and the address of a VkDescriptorPool variable to receive the new descriptor pool handle. So this will give us the memory where our descriptors will be allocated. What we need to do now is help define the binding structure of our descriptor set. This is defined inside of an object called a descriptor set layout, which creates the link between the descriptor set and the graphics pipeline. It once again specifies the descriptor count, which is our max textures, the descriptor type, which again is combined image sampler, but this time it also defines the binding location or index that we'll use to access the descriptors in the shader. In this case, we're saying that we only wish to expose them to our fragment shader. As you can see, our bindings are stored inside of an array of VkDescriptorSet layout binding objects, each of which would define a particular binding location. After producing this array, we can specify a separate parallel array of VkDescriptor binding flags, each one corresponding to a binding object in the other array. For our bindless textures, we'll make sure to enable the partially bound bit, which means that we don't have to update and bind all of the available textures in the set, but rather only the ones we need for the scene. And we also need to once again specify that we want to enable updating descriptors after binding, for the reasons we just discussed. Next, we need a VkDescriptorSet layout binding flags create info object, which just wraps our flags array into an object, letting us pass along the array's data address and the element count. Then we can create the descriptor set layout. We create an object of type VkDescriptorSet layout create info where we put everything together. The binding count is the size of our binding array. The p bindings is the bindings array address. The flags field has to specify VkDescriptorSet layout create update after bind pool bit, which will be important later when we allocate the descriptor set so that Vulkan can ensure that the descriptor pool and layout are compatible with one another. Also note that the pNext field is used here to pass the bindings flags, since the flags here are handled via the Vulkan API extension mechanism. Now finally, we call VkCreateDescriptorSet layout with the layout info object we just defined, and the address of a VkDescriptorSet layout variable to get the layout handle. The descriptor set layout now encodes everything that Vulkan needs to know about the types and quantity of descriptors involved. Now we can move on to creating the VkDescriptorSet allocate info object, which we'll use to create the actual descriptor set. Here we only need to specify which pool we'll be allocating from, the number of descriptor sets that we're going to be allocating, which is just one, and the layout that we want to use for the descriptor set. If we had more descriptor sets with varying layouts, then the pSet layouts field would have to point to an array of VkDescriptorSet layout handles corresponding to each set. And this would have to be the address of an array of descriptor set handles if creating more than one set. Since we're just creating one, we can just move on here. Now we can just call VkAllocateDescriptorSets with the descriptor set allocation info object and the address of the VkDescriptorSet variable for our new handle. This could also be the address of an array of descriptor set handles if creating more than one set. Now that we have our descriptor set layout and set objects, let's hop over to the createGraphicsPipeline method and make sure that the pipeline is expecting the descriptor set. The way we specify the types of descriptor sets we want the graphics pipeline to expect is by providing that information in the pipeline layout object. We previously just had an empty layout here, but this time we're actually feeding data into the pipeline, so we'll need to set up a few things. First, let's get the descriptor set stuff out of the way. We need to provide a list of descriptor set layouts, so we'll just put our new descriptor set layout handle in this array here. Then make sure that the pipeline layout create info object knows about it using the set layout counts field for the array size and the pset layouts field for the data pointer. While we're updating the pipeline layout, we might as well talk about push constants, which are a super convenient way of getting data into our shaders. Push constants are used for much smaller data as they're recorded directly into command buffers and usually encoded into high-speed GPU registers. You can check the maximum push constant size for your hardware using this code here, but we're not adding this to our codebase today as the minimum push constants requirement for Vulkan is 128 bytes, and we're only passing 24 bytes right now. When our requirements change here, we'll look at utilizing something like a descriptor uniform block, which can hold a lot more data. The way we specify the push constants that we're going to be using with this graphics pipeline is using a vk push constant range object. Here we specify the offset and size of our push constants, as well as the stage flags where the push constants will be exposed. At the moment, we're putting all of our push constants in a single object called frame constants, which will be exposed to both the vertex and fragment shader stages. This object is used to pass along the buffer device addresses for the data that we'll be using in the shaders, such as the vertex buffer address, materials address, and the render items, which we're going to look at very shortly. The push constants range is specified in the pipeline layout create info object here, where we say we have one push constant range at the address of the struct above. Since push constant memory is limited, it can be helpful to partition push constants data and expose it piece by piece to different shader stages, rather than trying to push it all at once to every stage. After setting this up, the graphics pipeline and layout will be created with full knowledge of our descriptor set layout and push constants. As you'll remember, we just call vkCreatePipelineLayout with the pipeline layout info and the address of our pipeline layout handle. With our work here wrapped up, we've seen how the descriptor pool, layout, and set are created, and we already covered how the actual update of our descriptor set happens when we updated the textures. We can now head back to the bottom of our load data method and wrap up there. The last item on our list here is to get all of the material data into a buffer that we can read in the shaders. There's not much new here, but there are a few things to call out. We've seen how to create buffers a number of times already, though this buffer is a little more interesting. Notice that here we have the storage buffer and shader device address bit set, meaning that it'll be used for general storage, and we want to get its address so that it can be read from directly in the shaders. This buffer is also created with the mappable flag set to true, which would mark it with the host access sequential write bit that we spoke about earlier, allowing us to write directly to it from the CPU. That, along with the VMA memory usage being set to auto, will likely result in this buffer being placed in the resizable bar region of VRAM, which is host accessible, as we know. Our materials are nothing more than a few numbers and texture indices, which are quite small in size, which means that this buffer will likely reside in the GPU's cache memory for the most part, making it very fast to access. Once we get our new material GPU buffer object, we'll add it into our buffers vector and get back its ID, storing it in a field for later. Finally, we can call our trusty memcpy method, which, as you'll remember, just maps the buffer, gets a pointer to it, and performs a memcopy of all of our materials into it. And with this, we're officially done loading, copying, and preparing everything for the renderer. Let's now head over to the render method, where we'll see how this stuff actually gets drawn. Most of the code in this method was thoroughly covered in the first video, including swap chain recreation, image barrier transitions, dynamic rendering, command recording, queue submissions, and so on. What we need to do now is prepare all of our data for the GPU so that we can submit everything for rendering. We'll start by computing a few matrices. We'll need these in a little bit when we're traversing our scene and computing every object's position. These are the view and projection matrices and the combined view projection matrix. The view matrix is responsible for transforming all objects from world space into view space, which is dictated by the position and orientation of our virtual camera. The way we produce a view matrix is using GLM's lookAt function. It receives the camera position, the camera's target, as well as a unit vector representing the up direction of the camera, which we're simply setting to the positive y-axis for simplicity. When you position a camera in the virtual world, it's not so much that your camera is actually moving, but rather what happens mathematically is the camera remains centered at the origin and everything else moves around it in the inverse direction, creating the illusion that the camera is what's moving. Move your head to the right and you'll see all objects in front of you seemingly moving to the left. This leftward movement of the objects is what the view matrix actually performs. If you don't move your head at all, but simply just move the objects just the right way, you can create the illusion that it's your head that's actually moving. The camera's position is calculated based on a few parameters, which we control with the keyboard. For the orbit camera that we're implementing, the parameters control the following. There's the yaw angle, which controls how much the camera turns about the vertical axis. There's the camera's pitch angle, which is the angle of our camera from the ground plane, which also ends up controlling the camera's elevation. Then there's the camera distance, which allows us to move it further or closer from our point of focus. In our orbit camera model, given the yaw and pitch angles, we can use some basic trigonometry to calculate a vector pointing to the camera's position along the unit sphere. This vector can then be scaled using the cam distance variable, allowing us to position the camera exactly where it needs to be. The pitch and yaw angles are used as the camera's spherical coordinates and represent a point on the unit sphere. Spherical coordinates are perfect for representing the position of an orbit camera. In order to get the Cartesian coordinates of the camera and generate a unit vector, we need to use our trig functions. To get the camera position's x-coordinate, we multiply the cosine of the camera's yaw angle by the cosine of its pitch angle. For the y-coordinate, we simply use the sine of the pitch angle, and the z-coordinate is the sine of the yaw angle multiplied by the cosine of the pitch. Multiplying the resulting vector by the camera distance gives us the final camera position. To control the angles of rotation and distance, we've introduced some basic key checks in the run method before rendering. First, the variables. Speed is just the generic value that we're using to determine how much rotation and movement to perform each frame. Epsilon represents a small value we can compare against, instead of just using a 0. We use this value as the minimum camera distance, preventing the cam position from ever becoming a 0 vector. Allowing this to happen creates issues in the GLM lookat function. The epsilon is also subtracted from the camera's maximum pitch angle, preventing us from rotating the camera to 90 degrees and beyond. Allowing the pitch to go beyond 90 degrees causes the coordinate system to flip and the controls become inverted, which we don't want. When the camera's pitch goes to exactly 90 degrees, the camera's view direction and up vector become collinear and cause a 0 vector to be produced by the lookat function, which results in an incorrect view matrix. Keeping this angle between negative and positive 90 degrees prevents this from occurring. To retrieve SDL's keyboard state array, we call SDL getKeyboardState before the run loop. Then inside the loop, we can check if the following keys are held. The A and D keys are used to control the yaw angle. The W and S keys control the camera distance, and the up and down arrow keys control the pitch angle. In each of these cases, we scale the speed value by the current delta time, and add or subtract the result from the corresponding angle or distance. If you've never written a game loop or have never heard of delta time, I've put a link in the description to my Game Dev from Scratch video, where we look at how to write a game loop and calculate delta time. The gist of it is, to calculate delta time, at the start of each frame, we call SDL getTicks to get the current time in milliseconds, storing the result in a 64-bit unsigned integer named nowTime. We also have another integer of the same type called previousTime, which captures the previous frame's start time. If we subtract the two, we get the number of elapsed milliseconds between the start of the previous frame and the start of the current one. Dividing this by 1000 gives us that same time, but expressed as a fraction of a second. Our speed variable expresses how much we want to move per second, so multiplying that speed value by our delta time tells us how much we should be moving during the current frame. After we've calculated delta time, our current now time is stored in the previous time variable, so that it can then be used in the next frame's calculation. Note that the yaw, pitch, and distance variables are stored as float fields in the application, and the yaw angle is initialized to a value of pi over 2, or just 90 degrees. We're expressing our world in a right-handed coordinate system, which is consistent with GLTF's coordinate system, as well as Vulkan's NDC coordinates. To understand why it's called right-handed, take your right hand and extend your thumb, index, and middle fingers in a way so that they form 3 axes. Point your thumb to the right, which would be the positive x direction. Then your index finger points upwards, representing the positive y direction. If you then extend your middle finger, it would point towards you rather than into the screen. This is the positive z direction in a right-handed system. Rotating the camera over to 90 degrees places it at the positive z-axis, looking down towards the negative z direction, which we just established is actually the direction towards the screen. If you do the same exercise with your left hand, your middle finger would point away from you, showing you the difference between a right and left-handed coordinate system. With an understanding of the orbit camera and coordinate system, it's easy to see now why the view and projection matrices are calculated using the right-hand variants of these functions. Next, we need to compute the projection matrix, which is responsible for producing perspective in the 3D scene, and is what ensures that as objects get further away from the viewer, they get smaller and converge. GLM's perspective function requires a few parameters, so let's go over them. First is the vertical field of view, which dictates the vertical angle of the viewing frustum. This parameter is expressed in radians, which we're creating using GLM's radians function and setting to 75 degrees. Next, we provide the horizontal aspect ratio, which is computed by dividing the width by the height. The result of this, together with the vertical field of view parameter, are what ultimately dictates the horizontal field of view. Increasing the vertical field of view ultimately also increases the horizontal field of view if we don't change the aspect ratio. The last two parameters control the near and far planes of our viewing frustum. Vertices outside of this range are clipped by Vulkan and not rasterized. The far plane can be used to control the draw distance of our renderer. Note that we don't need to compute this matrix every frame. You could move this calculation so that it only happens when the window size or resolution changes, or if the vertical field of view is changed. I'm just doing it here for simplicity and so that we can have everything in one place to look at. Once we have the view and projection matrices produced, we multiply them together in this order to get our combined view projection matrix. As we discussed earlier in the video, matrix multiplication order matters, as our vertices will be multiplied on the right side of the matrices. Multiplying in this order ensures that the view transformation occurs before the projection transformation. Now we're ready to start processing the scene nodes and rendering. As we go through all of the scene objects, we don't simply call a Vulkan draw function for each object. You could certainly do this, but like everything else we're doing, we're going to approach this in a more efficient and modern way. Instead of calling draw for each object, which has to pass through the graphics driver for each draw call, we're going to record the information for each of the draw commands in a buffer and then hand that buffer directly to Vulkan in a single draw. Once the GPU has the list of draw commands, it'll have everything it needs to draw all of the objects without any more involvement from the CPU. This technique is called Multi-Draw-Indirect, or just MDI for short. First, we'll need to head over to the createDevice method and make sure we have support for it, though MDI support on desktop is excellent. Next, we'll have to create a couple of buffers for this for each of our frames in flight. This happens in the createIndirectBuffers method, which is called at the end of the initializeVulkan method. For each of the frames in flight, we first create a buffer to hold the multi-draw-indirect commands. Once again, we're using the createBuffer method, but this time we're setting the buffer usage to indirect buffer bit. The size of the buffer is just the maximum size of our NodeWorld, multiplied by the size of the vkDrawIndexedIndirect command, which is the struct we'll be storing our per draw call information in. This buffer is also flagged as mappable, as we'll need to write to it from the CPU, and the VMA memory flag is set to auto. Once we get the newly created GPU buffer object, we store it directly in the frame resources object, so that we can access it during rendering directly. We also need to map the buffer so that we can get a direct pointer to its memory. We then cast the pointer and store it in the frame resources object as well. Next is the render items buffer. As we draw each object in the scene, we're going to want to provide some more info about it to the shaders, such as its transformation matrices and associated material index. This data is stored in the render item struct. We'll see how that gets used inside the render method. The procedure here is similar. The buffer size is calculated, then createBuffer is called. Except this time, we create a generic storage buffer and also enable BDA to get the buffer's device address. We need this address since we're going to be reading from this buffer in the shaders ourselves, unlike the previous buffer here, which only Vulkan will be reading. Once again, we map this buffer and get a pointer to it for use when writing from the CPU. Note that both of these buffers are kept mapped long term. This is why you don't see an unmapped call here. This way we can avoid the overhead of mapping and unmapping their memory every single frame, which reduces overhead. If we take a look at the application's shutdown method, we'll see that the buffers are first unmapped there before we destroy them and free their allocated memory. Now it's time to record the draw commands. To visit every single node in the scene, we can use another recursive method, but I prefer not to use recursion here on the hop path. We're going to opt for a stack-based approach here instead. The stack itself is simply just a vector, and each element is an STD pair. The pair itself holds a pointer to a node object and a 4x4 matrix. Each node's associated matrix here is its parent global transformation matrix. Let's see how this is used. First, we need to push the scene's root nodes to the render stack. This will be the set of nodes we'll start processing from. We retrieve each root node from the NodeWorld and create a pair containing its memory address and the matrix representing its parent's global transformation. Given that these nodes are at the root of the scene, there is no parent transformation, so we just use an identity matrix for each one. As we've seen before, we iterate through the nodes by following their next sibling ID links until we find a null link ID. Next, we start the while loop that records all of the draw call information. It will iterate while the render stack is not empty. Given that we've pushed the root nodes into the stack and will iterate through all of their children, the stack will contain elements until we finish the entire scene. We start off in here by grabbing the item at the top of the stack and then popping it off. This gives us back the pair containing the pointer to the scene node and its parent's global transformation matrix. Now we have what we need to calculate this current node's global transformation. You'll recall from earlier that the node's getTransform method will either return the cached local transformation matrix or calculate it from scratch, cache it, and then return it. To get the node's global transform, we simply multiply the local transform by the parent's global transformation, and we get the node's global world transformation. Now we can move on to the MDI draw commands and the render item object that accompanies each draw operation. We do have to make sure that the node actually has an associated mesh, otherwise we can skip rendering it and simply move on to processing its children and adding them to the render stack. If there is a mesh to render, we use its ID to index into the global mesh vector and retrieve a reference to the mesh object. Since mesh objects are just a collection of drawable submesh objects, we need to iterate over each submesh and ensure it's rendered with the appropriate material. Each submesh defines a subset of vertices and vertex indices comprising the submesh's geometry inside of our global geometry buffers. To record the draw command details, we create a VkDraw-Indirect command object with the following fields. The index count field is the number of vertex indices comprising the submesh, which we set to the index count field of our submesh. We keep the instance count field at 1, as we're not dealing with instance mesh rendering just yet. We're going to look at this in a separate video. The first index field specifies the global index of the first vertex index of the submesh, which receives the index start field. For the next field, it's important to remember that every submesh contains indices that start from 0, which makes every index relative to the vertex data specific to a particular submesh. This means that we can't use them directly to index into the global vertex buffer. This is where the vertex offset field comes in. Vulkan will add this offset to every single index that goes through the vertex shader and store it in a special variable called GLVertexIndex, which we can then use to grab the correct vertex from the global vertex buffer. We're going to see this in the vertex shader in a second. The first instance field is normally used when you want to draw instances of a particular mesh multiple times. Though, like I said, we're going to revisit this topic separately when we look at something like drawing many trees, grass, or rocks. For today's purposes, this field simply represents the index of the draw command for each submesh in the scene. The draw index variable outside of the loop starts at 0 and is incremented each time a submesh draw command is recorded. This is why we're using it to index into both the MDI draw command buffer and the render items buffer. Since we stored pointers to both of these buffers in our frame resources struct, we can use those pointers directly and write our objects by indexing directly into them. Next, we create the render item object to accompany the current Vulkan draw command. Here, we write the node's final worldview projection matrix by multiplying the node's global transformation matrix that we calculated above with the view projection matrix that we computed before we started the loop. This gives us the worldview projection matrix, which is often also called the model view projection, but I tend to prefer the word world here since it's a world transformation, not so much a model transformation. We're transforming into world space. We also store just the world transformation matrix without the view projection baked into it. This matrix will be needed for our directional lighting in the shader. Finally, we convert the submesh's material ID into a material index, which you'll recall just means subtracting a 1 from the ID. We're going to use this index inside of the shader to grab the appropriate material. After creating the draw command and render item pairs for each submesh, the draw index variable is incremented and we move on to the next submesh. After all of the mesh's submeshes have been processed, we can move on to pushing the node's children onto the stack for processing as well. The first child ID of our node is stored in a variable called childNodeID, and another loop is started. This time we follow each child's next sibling ID link and iterate through all of the node's children. First, the child node is retrieved and a new pair is pushed onto the render stack. This time we push the child node's memory address, along with the world transformation matrix that we computed for the parent node above. And this is how we ensure that all child nodes incorporate their parent node's world transformation and maintain the spatial hierarchy. Once we're done pushing and popping nodes to and from our render stack, we can move on to preparing the data for the graphics pipeline. We can skip over the code that begins the command buffer, performs the swap chain image barrier, and prepares the dynamic rendering structures. We've gone over all of this in the first video. What we need to do now is ensure that our global descriptor set is bound, which is how the image descriptors that we wrote earlier will become exposed to the graphics pipeline. This is done by calling VkBindDescriptorSets. We're binding our global descriptor set for use with the graphics pipeline, so the bind point is set to graphics. The graphics pipeline layout also needs to be specified in the next parameter. Since we're binding only one descriptor set, we'll set the first set parameter to 0 and the set count to 1. Then we can provide the address of our global descriptor set. We're not using the last two parameters here for now, so we can just set them to a 0 and a null. They would be useful if we wanted to dynamically offset into some large buffers that are being exposed to the shaders via descriptors, which we're not doing for the moment. With the descriptor set bound, any pipeline we use for rendering after this will be able to see the global descriptor set along with the image descriptors. Now we also need to provide the push constants data as well. You'll recall the frame constants object we looked at earlier, which is the structure that holds the buffer device addresses for the vertex, material, and render item buffers. The vertex and material buffer IDs are stored in the application, so we can just look up the buffers, get their device addresses, and store them in the respective fields in the constant struct. For the render items, remember that each frame in flight has its own buffer. So we retrieve the buffer from the current frame's resources and store its device address in the constant struct as well. Now it's just a matter of calling vk command push constants and passing the following parameters: the current frame's command buffer, the pipeline layout we're using, the shader stages where we want the push constants data to be visible, an offset into the push constants memory, which we'll just set to 0 since we want the whole struct, and of course the size of the struct. Then finally, the actual address of the frame constants object itself. Unlike many command buffer recording functions, this function actually writes the push constant data immediately into the command buffer. This means that we don't have to worry about the lifetime of the frame constants object, such as keeping it around long enough for the command buffer to execute, which is why we can get away with a stack-based allocation of the frame constants object here. The last bit of data that we need to provide here is the global index buffer. As you saw, each draw command specifies a range of indices that make up the submesh we want to draw. In order for the indices to be available to the draw commands, we need to record a command that will bind the global index buffer prior to executing the draw commands. We first retrieve a reference to the global index buffer using its cached ID, and then record a command to bind it. This is done with the vkCmdBindIndexBuffer function. It needs the command buffer, of course, the vkBuffer handle of the index buffer, an offset into the index buffer, which we'll keep at 0 to use the entire index buffer, and the size of each index, which we established are 32-bit unsigned integers earlier in the video. Now we can begin dynamic rendering and submit the data for the draw commands to the GPU. I'll skip over the viewport and scissor sections for now, but we'll come back to it after looking at the shaders, as there are some important details to discuss here. What I want to highlight for now is just the bind pipeline command here, which we've already seen and discussed in the previous video, and the draw command. The call to vkCmdDraw_Indexed_Indirect is what submits the required draw operations to the GPU. It takes the command buffer, the indirect draw vkBuffer handle, the start index within the buffer, and the number of draw operations we recorded. Remember that draw index was incremented for each submesh we process, so it holds the total number of submeshes that we're actually drawing. We also provide the size of the vkDrawIndexIndirect command struct, which is used as the byte stride between the draw commands. If the objects weren't tightly packed in the buffer, you'd use whatever other byte stride you require. Ours are tightly packed, so we use the actual structure's size. Now, while the descriptor set, push constants, nodes, and indices are hot in our brains, let's dive into the shaders and tie everything together. We'll skip over the extensions at the top for a little bit to get to the important bits. We'll come back here as needed. First off, we need to tell the shaders what our frame constant structure looks like. This is done using this uniform structure here, also named frame constants. The C struct and GLSL names don't need to match, but it doesn't hurt to keep things consistent. The fields are the same as the C struct and ordered in the same way. These are the 64-bit integers representing the buffer device addresses that we looked at previously. In order to use the 64-bit unsigned integer type, the GLEXT shader explicit arithmetic types int64 extension needs to be declared at the top, and we need to ensure that we have support for it and enable it during device creation. To read in the data from the buffers pointed to by the device addresses in the frame constants, we'll need a few structures and buffer references. First on the list is the Vertex structure. This matches our C struct counterpart with its position, color, normal, and UV fields. In order to access the Vertex data, we need to tell GLSL what we're going to be expecting at the Vertex buffer's device address, which will of course be an array of vertices. We do this with the buffer section here. The layout qualifier allows us to specify that this will be a buffer reference, and the scalar qualifier here sets the memory layout rules. Traditionally in graphics APIs, one of the pain points is ensuring the memory layout of our C structures, such as our vertices, map over correctly to their shader structure counterparts. C and GLSL structures have different memory alignment rules. So graphics devs have to introduce padding and careful ordering of fields to prevent memory from becoming corrupted. Imagine we have a C struct that contains 4 float fields, followed by a vector 4. The floats would be aligned to 4-byte boundaries, and the vector 4 would start on a 16-byte boundary. If we then have another float followed by a vector 4, then we would have an issue. The C data is tightly packed together, so the vec4's memory is immediately after the float's memory. Whereas in GLSL, the compiler would start the vector 4 on the next 16-byte boundary. This means that in order to have the vector 4 in our C structure translate correctly to the GLSL's memory, we have to add 12 bytes of padding after the float, but before the vector 4. This would cause the C struct's memory to line up correctly with what GLSL would expect. Another solution is to reorder the fields so that the vector 4 is placed before the float, which removes the need for any padding. This requires careful planning and is often a cause of bugs for beginners. Nowadays, we have the scalar memory layout, which relaxes the memory boundary rules where instead of 16-byte boundaries, the vector 4 would be placed based on the size of its components, which would be 4 bytes. This is what makes it possible for us to easily use the vector 3 fields you see in the Vertex structure. Normally, we would need to include 1 byte of padding after each field in the C structure in order for the fields to map correctly to the shader structure, which would have been aligned to 16-byte boundaries. Using the scalar layout means each vector 3 now has to align based on the size of its scalar components, which are each 4-byte floats. This completely removes the need for any padding. It's still worthwhile to read up on the standard memory alignment rules though, and the Vulkan documentation has an excellent write-up on this topic. Be sure to check that out. To be able to create this buffer reference, we need to specify the GLEXT buffer reference extension at the top of the shader source. For the scalar block memory layout, we also include the GLEXT scalar block layout extension. Both of these also need enabling during device creation. The scalar block layout is enabled here, and the buffer reference extension is enabled with the BufferDeviceAddress features. For the materials buffer, the pattern is the same. We introduce a struct representing the material data, mirroring our structure on the C++ side. This includes an RGBA vector 4 for a base color and an unsigned int for the base color texture index. And like the Vertex data, the material pointer buffer reference is what we use to get the materials data array. Render items are the same story. Here we see the world view projection matrix, the world matrix, and the material index for the object we're rendering. Again, we define a buffer reference in the form of the render item pointer, which will give us the array of render items. Jumping into the body of the main method, we can see how the buffer references are used. First, we create an instance of Vertex pointer and pass it the Vertex buffer address from our frame constants. This creates an instance of the Vertex pointer buffer reference and lets us access the Vertex data. To retrieve the vertex for the current Vertex shader invocation, we use the GLVertexIndex built-in variable. Recall that this variable is provided to us and is the sum of the draw command's vertex start offset and the current vertex index. This sum gives us the absolute index of the vertex within the global vertex buffer. The variable v here is an instance of the vertex structure, and we can now retrieve the various attributes directly from it. The render items pointer is instantiated the exact same way, but to get the render item for the current object, we have to index into the render items array using the built-in GLInstanceIndex variable. Since we don't have multiple instances of our objects, as we haven't yet covered instancing, each object only has a single instance. So the instance index variable increases by 1 for each draw operation, which means that we can use the instance index value to index into our render items array. To get the material associated with this draw, we instantiate the material pointer buffer reference, and then index into the materials array using the material index value stored inside the render items object. Now we have the vertex, render item, and material objects for the current shader invocation, which is everything we need to complete our work here in the vertex shader. First, we'll calculate the final vertex position. Multiplying the position with the world view projection matrix we stored in the associated render item object moves the vertex into what is called clip space. The graphics pipeline uses this to clip geometry and only rasterize the portions that are visible in our view frustum, ensuring that we don't try to shade things that are not visible on screen. After this, it performs what's called a perspective divide and moves the points into normalized device space. This is what ends up giving our objects perspective. One thing to consider is that our vertex here is a vector 3 and the matrix is a 4x4 matrix. So we need to create a vector 4 and we place a value of 1 for the fourth component prior to multiplying. The 1 is important as the vertex is a point in space, and the 1 here ensures that translations encoded in the matrix contribute to the vertex's final position. Now we'll write the output variables of our vertex shader, which we'll expect to receive in the fragment shader. Remember that the location values of each output variable must match the corresponding input variables in the fragment shader. We'll start with the vertex color. We simply copy it over from the vertex attribute into the output. These vertex colors will be interpolated for each fragment produced by our vertices. In order to shade the triangle in the fragment shader, we need to ensure the vertex normals are correctly transformed as well. We don't apply the full world view projection transformation on the normals though. The normals tell us which way the surface of an object faces, which dictates how much light it should receive during the fragment shading. This means that we only care about its orientation in world space. We have to be careful about how we transform the normals, as they shouldn't be translated given that they're only directions in space, and not points in space. They can also end up pointing the wrong way if they're transformed by a non-uniform scaling matrix, which results in normals that are no longer perpendicular to the surface. Taking the transpose of the inverse of the world matrix gives us a matrix to transform our normals. This matrix ensures that the normals remain perpendicular to the surface regardless of non-uniform scaling or shearing transformations. We also construct a 3x3 matrix from the 4x4 world matrix, which essentially cuts away the translation values from the matrix, preserving only the rotation and scaling encoded in the matrix. Multiplying the normal by this matrix and storing it in the output variable gives us what we need. Next, the UV coordinates are also copied into the output variable. The last two output variables are flagged with the flat qualifier. One is the index of the color texture we're going to be sampling in the fragment shader. The other is the flat base color of the material. Normally when we write a value to an output variable in the vertex shader, the rasterizer stage interpolates those values and produces interpolated input values for the fragment shader. We saw this with our triangle in the previous video, which had various colors interpolated across its area. This is important since for every 3 vertices making up a triangle, there could be thousands or even millions of fragment shader invocations required to rasterize the triangle. Since the fragment shader is invoked orders of magnitude more times than the vertex shader, we can perform certain tasks in the vertex shader rather than in the fragment shader, such as looking up the material and retrieving its color and texture index data. Reading the data in the fragment shader wouldn't be so bad thanks to the GPU's memory cache, but it's objectively better to access the material buffer memory 3 times in the vertex shader versus thousands or more in the fragment shader, regardless of whether it's from VRAM or the L1 cache. What the flat qualifier does is prevent output values from being interpolated across the fragments. The texture index and material color we write here for a given triangle are consistent for the entire triangle, so it makes no sense for us to let the rasterizer even try to interpolate them. And with that, our work in the vertex shader is done. It's time to jump over to the fragment shader. We start off the fragment shader with the extension that we'll be needing to work with the image descriptors. The GLEXT non-uniform qualifier extension is what allows us to use a non-uniform value to index into the texture samplers array. Normally, we're required to use a uniform value when indexing into a descriptor list, and a uniform value is one that stays constant or uniform for the entire draw call execution. Changing a uniform value requires us to stop and bind a new one on the CPU before we continue drawing, which isn't possible since we're using Multi-Draw-Indirect. Our texture index input variable is marked as flat, so it's constant only for the current primitive or triangle we're currently shading. This is why in order to use it as a sampler index here, we must ensure the non-uniform qualifier extension is enabled. Looking at the Vulkan 1.2 feature struct in the createDevice method, we also want to enable the following. First, the shader sampled image array non-uniform indexing feature. This is what lets us use non-uniform indexing in the shader, allowing us to use our flat texture index input variable instead. Then we have descriptor indexing. This allows us to index into our texture sampler descriptors altogether and is the foundation upon which the entire bindless texture approach is built. Next, we have descriptor binding sampled image update after bind. This feature allows updating of descriptors even after the descriptor set has been bound. Next, we have descriptor binding partially bound. Normally, you need to update all of the image descriptors you specify within a descriptor set. We obviously wouldn't want to do this with the bindless texturing setup, as we can allow for tens of thousands of image descriptors in our descriptor set. This feature lets us update and use only the image descriptors we need for our scene or game levels, rather than having to update and bind the total maximum allowed. Finally, we have runtime descriptor array. This one lets us declare our textures array without specifying its size statically in the shader. This way, our resource maximum is dictated by our engine runtime rather than our shader code. Back in the shader, we don't need to go over the input variables as we just finished talking about them. Just remember to triple check the location index values and make sure they match up with what you're sending out of the vertex shader. This output variable here, though, is important, and we saw it in the previous video. Its index maps to the color attachment index we specify in the dynamic rendering setup, and is how we write the color data into the swap chain image. Next, we have our descriptor set, or more specifically, the combined image and sampler descriptors that we wrote. Here, we state that we're expecting our uniform array of sampler 2D objects. They're called sampler 2D because they combine a sampler and a 2D texture resource together. Since our global descriptor set is the first and only set we bind, its index is 0, and the combined image and sampler descriptor array is the first and only binding, so it also gets an index of 0 here. Once inside the body of the fragment shader, we use the GLSL built-in texture function to sample the texture image. This function takes the sampler 2D object, which we can retrieve by non-uniform indexing, into the textures descriptor array using our texture index input variable. Of course, we also need to specify the UV coordinate we wish to sample at by passing our UV coordinate input variable for the second parameter. This will sample the appropriate image using its associated sampler and give us a vector 4 containing the color value. We could have just written this color directly into the frag color output variable, which would have wrote it to the swap chain image attachment, and our work would have been finished here. But I did promise a small bonus lighting snippet to help make your scenes less flat and give you more to play with. Remember that we're going to go over lighting properly in the next video, so today we'll just quickly gloss over this lighting code. What we're doing here is creating a simple directional light, which delivers the same amount of light throughout the entire scene, making it great for imitating sunshine. First, we need to prepare our normal vector. When passing the vertex normals through the output variable and into the fragment shader, the normal vector is interpolated across the surface of the triangle being shaded, giving us the specific normal for the current fragment of the triangle being rasterized. This interpolation, though, can cause normals to no longer be of unit length, which is why we need to make sure that we normalize the vector before using it. It's critical that our surface normal is a unit vector before we try to perform any lighting calculations. Next, we specify the direction of the light, which is pointing downwards and into the screen. Since the coordinates provided here don't specify a unit vector, the light direction must also be normalized to ensure its length is 1. Now we can calculate how much light the current fragment should receive, given its surface normal and the direction of the light. To do that, we need to consider the angle between the surface normal vector and the incoming light vector. We also need to consider, though, that the light direction vector is inward, towards the object, and a surface normal is a direction pointing away from the surface of that object. One vector points inwards and the other points outwards. If we negate the light direction vector and flip its direction, then we'll have two vectors each pointing outwards. Taking the dot product of these two vectors gives us the cosine of the angle between them. An angle of 0 between the two vectors results in a cosine value of 1, meaning that the two vectors are pointing in the same direction. This also results in the strongest possible incoming light. As the angle increases towards 90 degrees, the cosine value decreases to 0. As the angle goes beyond 90 degrees, this means that the light is now pointing to the back of the surface, causing the cosine value to go into the negatives. We don't want negative light values in our calculation, so we clamp the bottom end of that range to 0 using the max function. The value now stored in the variable d can be used to scale the color intensity of the fragment depending on its direction relative to the incoming light. A value of 0 here, though, can result in dark areas when surfaces are pointing away from the light. This doesn't look very good, as in reality, most surface will receive at least some light due to indirect light bounces. We can mimic some of this using some ambient light in the scene. Here we're specifying the colors of a two-tone ambient light. One can be our sky color value and the other the color closer to the ground. Both are very low intensity, as we don't want the ambient light to blow out the colors of our scene. We interpolate between these two colors using the y component of the surface normal. The range of this value is -1 to 1, though, since the normal is a unit vector. What we need is for it to be in the range from 0 to 1. This can easily be achieved by multiplying the y value by 0.5 and then adding 0.5 to it. Storing the result in t, we then use this value to get the interpolated ambient color using the built-in mix function, and the value t serves as the interpolation factor. Before we apply the lighting, we first calculate the final unlit color value of the fragment. We factor in all of the various sources of color, which gives us quite a bit of control. We have the vertex color, which defaults to fully opaque white unless otherwise specified in the vertices. We have the sampled color value, and we have the color specified in the material used for the object. Multiplying the three colors together gives us the final color. If we wanted to change the color tint of the textured object, we could easily achieve that by changing the color of the material used. Next, we calculate the color of the surface after the lighting has been applied. We use our value d from above to scale the intensity of the lighting, giving us a darker or lighter shade depending on the surface direction. We add to that color our final color once again, this time multiplied by the interpolated ambient color, which adds a little bit of color intensity to the areas that would otherwise be very dark. Now we can store the final lit color to the swap chain image, which requires a 4-channel color. What we do is create a vector 4 from our lit color value and take the alpha value from the sampled texture color, which produces the final color value that we write to the swap chain image. And with that, we're done covering the fragment shader. If you're following along and run your application now, you'd likely find that your rendered scene is upside down. In Vulkan, the negative y direction is up, and in general for most meshes and tools, the negative y goes down. There's no problem with our renderer, this is just a normal symptom of Vulkan's normalized device coordinates. Developers often address this by flipping a y-coordinate in the projection matrix, but that has the added effect of reversing the triangle winding order, causing front faces to become back faces and vice versa. The right way to approach this is by flipping Vulkan's viewport, as it doesn't affect the winding order and is officially the correct way to flip the final image. First, we'll set the top boundary of the viewport, which is done by setting its y value. We set this to the swap chain's height value. Then we make the bottom boundary of the viewport be the top of the screen, at a y-coordinate of 0, essentially flipping the viewport's direction. Vulkan calculates the viewport bottom boundary by adding the viewport's height to its y-coordinate. If we set the height of the viewport to the swap chain's negative height, then adding its height value to its y-coordinate will result in a 0, which is exactly the coordinate we want to represent the top of the screen. If the viewport has a top boundary set to the swap chain's height and its bottom boundary set to 0, we essentially ask Vulkan to flip the final image. The last thing we need to remember to do is clean up all of the resources during the application's shutdown. This includes the descriptor set layout and descriptor pool. We don't need to destroy the descriptor set itself as it's allocated from the pool. Next, we free the memory used by images and image views, which we created for the loaded textures. Then we destroy the samplers. We also need to destroy the buffers we're still using at the end of the application, as well as the buffers we allocated per frame in flight for the indirect draw commands and render items. And finally, there's the command pool we created for the transient command buffers we've been using. That about covers everything. I hope everything was presented clearly and was easy to follow. We covered a lot today, and I hope many of you got through the whole video. Be sure to tell me what you're working on or suggest ideas for future videos. I love hearing from everyone, and the positive feedback has been absolutely amazing. As always, thank you for watching and look out for the next video.